microscopes. And light microscope, this is light microscope, and use this light microscope, you can see particles up to in the range of 1 micron. But when you go to electron microscopes, these electron microscopes give much higher resolution than the light microscopes, and you can very easily obtain the magnifications of more than 1 million times. And you can see this using this light microscopes, you can see up to red blood cells. And but of course, by using these electron microscopes, either scanning electron microscopes or transmission electron microscopes, you can see particles which are in the size range of 10 nanometer or even 2 nanometer to 100 nanometers and more. And how big is a nanometer? And just consider a human hand skin. Now, this particular small area, 1 by 1 centimeter is magnified, and you see this is the image. And when it is zoomed down to 1 centimeter, and you see the small wrinkles on the skin, will be able to see. And if it is further zoomed down to 1 millimeter, then you can see it very beautifully here. And if it is further reduced to 100 microns, then you can see it very, very nicely. And then if it is further magnified, then you can even see white blood cells. And then if this white blood cells is further zoomed down, then you will be able to see even the DNA molecules, which are about 100 nanometer size. And if this small part of this DNA molecule is magnified using a transmission microscope, then you will be able to see even the atoms. And there are a number of things living organisms which are I'll just take out this particular photograph and now fly. And if this particular head is scanned at the 100 micrometers range, and then we'll be able to see this structure. And then if it is further zoomed down and then magnified, and then you'll be able to see even the sensors, sensor buds, what you call as sensor buds. And this sensor buds, if it is further scanned, then you'll be able to see this DNA molecules. And before I start my presentation, I would also like to tell you that this nanotechnology is not a new one. And in medieval period and 13th century, and in Romans and the Chinese and everywhere, everybody were using this nanotechnology. I do not know whether they used knowingly or unknowingly, but then there were many reports in the literature suggesting that as early as in the 13th century, people have started using these nanomaterials and their manipulation. And you have heard about this famous Tipu Sultan sword. And he's a very famous king, and then he used a sword, and then it is still preserved in the museum. And people are very much curious about knowing this about this particular sword, because this even after hundreds of years of existence, people say this particular sword is not rusted, and then and then it cuts objects very sharply and so on. And also, the earlier peoples in the olden, in the earlier centuries also have used this Pandavastam. People used to take gold and then grind it and then reduce to nanometer scale, and then consume, and then so that will give them some color enhancement and so on. So therefore, at least from these examples, we can say that This nanotechnology and nanoscience is not something new, but this has been used previously by different people throughout the world. And then you can, I will just show you a few slides just to make you understand this, the nanomaterials in nature. Okay, and everywhere, people or the living organisms, they use this nanomaterial. I mean, it is in their process. And here, these different flies are there, and the different parts of these flies are in different colors. And the reason is that on their wings, there are small pigments like materials in the size range of nanometric range, and so therefore light falls on their wings, and these different sized nanomaterials reflect light of different colors, and so therefore when we look at them, we see them in different colors. Okay, and then this again is the similar thing. Then why people are talking so much about nanomaterial? And as I shared with you in my first slide, materials became differently at this scale. Okay, and the size matches, size and the shape of these nanomaterials matter most. If you are able to manipulate the size and shape of the nanomaterials, then you can really do a lot of things with these nanomaterials for different applications. And suppose you take gold, and this is, let us say, this is a bulk gold, and it is yellow in color. Bulk gold is yellow in color, and if you divide this bulk gold into very small micrometer range, even in the micrometer range, the gold continue to look in yellow color, because that is what we see. And if it is grinded, and then if you bring the size of the gold nanoparticles down to 100 nanometers, then you will be able to see gold in different colors. And these are all the colloidal solutions of gold nanoparticles, and you see this colloidal solutions in different colors. What is there inside is gold nanoparticles in different colors. Okay, so this is yellow in color, and this is pink in color, blue and dark blue, and red and wine red. And so therefore, the different size of the nanomaterials, if you are able to synthesize, then the optical properties of these materials will be enhanced tremendously. And these are the copper nanoparticles prepared in different sizes, and the colloidal suspension is taken in different test tubes, and you will be able to see this copper nanoparticles in different colors. And but then the copper nanoparticles or iron nanoparticles or silicon nanoparticles, whatever materials you take in the bulk size, they will appear in their original color. But then when you use any technology or any synthesis route to reduce them in the nanometer range, then you'll be able to see them in different colors. And these are the colloidal dispersants of iron nanoparticles, and then this iron nanoparticles are prepared in different colors. Then you'll be able to see them in different colors. And this is cadmium selenide nanoparticles, and once again, with their color changes, you can understand that this cadmium selenide nanoparticles are in different sizes. And these are some of the images of the silicon nanoparticles, which are prepared in different colors, in different sizes. Now, why the different properties for different sizes? One of the most important thing about these nanomaterials is these nanomaterials have large volume to surface ratio. It is because of this large surface to volume ratio, these nanomaterials are being used in number of applications, because these nanomaterials are reduced to a nanometric range, and since they are reduced to the nanometer range, you will be able to see them. You will be able to prepare these nanomaterials with the different physical properties, different chemical properties and magnetic properties, optical properties, and electronic properties, and so on. So the thing is that these nanomaterials have got large surface to volume ratio, and to just technically some kind of interest in nanomaterials and nanomaterial based product, I thought I could introduce this slide. And this is taken from Nature Biotechnology. And if you look at this particular graph, and you will be able to see from the year, though these nanomaterials are known to the humankind in the very early stage, but then very systematic way of using these nanomaterials have started in 1990s. And just 3 decades back, this nanomaterials research got widespread attention because of these peculiar properties of these nanomaterials. And many products have been found out, and then patents have been applied, and consequently, number of publications in these nanomaterials-based nanomaterials have also increased exponentially. So therefore, if you look at this particular slide, and then you will be able to understand how much interest is being generated because of this size and shape dependent properties of these nanomaterials in the research community. And this is a particular projection by industry group, and they have projected in the year 2015. So 15 years have gone by, but then still at least this was projected very long time back in 2008. And they say this industry, nanomaterial based industry, will become $1 trillion industry. And okay, so you see always nanomaterials are used in material science and electronics and pharmaceutical industry, chemical manufacturing industry, aerospace industry, and healthcare industries. And okay, so everywhere people have using these nanomaterials. And these are some of the products which have been developed using this nanomaterials. And now what you see is baseball and some lotions and then cricket rackets and then helmets. And the very interesting thing about these products is that if you incorporate nanomaterials in making these products, then your products will become lightweight and stiff at the same time, durable and neat. And also people have started using these nanoscale thin films on eyeglasses, that is in your specs, and then in computer and camera displays, and in windows and many surfaces. And so this will make them water repellent and self-cleaning, and then will be resistant to ultraviolet and infrared light. And then they will exhibit antimicrobial, anti-fog properties, and scratch resistant, and so on. And of course, these products, some lotions and other things have also been in the market of late. And then there's sunscreens and cleaners, and then creams and lotions and shampoos. Okay, so all these items are now making use of these nanomaterials-based products. And not just that, now people have also manufactured nano jeans, nano fabrics, and it is gaining wide popularity because if you could make nano material based fabric, and then what they say is these fabrics will be wrinkle free, and then water repellent and stain free, and then odor free, okay, and antibacterial resistance also this will have, and then they will block UV rays. And so therefore, because of all these properties, and people say nano fabrics, once nano fabrics comes into the market, I mean it is already in the market, but then so maybe when it is affordable to buy, and then people will be able to buy it, and then what they say is once you buy it, and then they say even you don't need to wash it, and then you don't need to even iron or okay, plus. So therefore, these are some of the advantages of nano fabrics, and also this in the car industry also people have now started using these nanomaterials, And even you can know people. There are some reports in the literature saying that even
கான்ஃபரன்ஸ் போயிட்டு இருக்கு. ஒரு ஃபெலிசிட்டேஷன் பேசி முடிச்சிட்டேன்.
And what they say is even one needs to be able to make a nanocar, and people say this nanocar will be much lighter than the human fiber who is inside and in the car. And the fuel efficiency also. Nowadays, fuel cost is skyrocketing at more than 100 rupees per liter, and so therefore maybe it will take another tens of years, maybe in the later generation of the people will be able to realize these nanoparts and so on. And also these nano sensors are also now being used in different industries, and especially in food industry. Now these nano sensors are being used, and these nano sensors can warn people against spoiled food. And okay, so therefore these nano sensors can also be used using these nano materials. But of course, this nano, water purification, water is a global crisis, and these silver nano materials. You have got different, filters are available now to filter to get good water. But in many filters now people are using the silver-based nano materials, and to make it a little more drinkable. And so therefore this also is one of the very much interesting implications of the nanomaterials. And there are different depending on the sizes. These nanomaterials have got different dimensions, and you have zero-dimensional nanomaterials, and one-dimensional nanomaterials, two-dimensional nanomaterials, and three-dimensional nanomaterials. And you can prepare each of them. Each one of them can be prepared in the laboratory by very carefully controlling the experimental conditions. And these are some of the nanomaterials which are reported in the literature. And you see these nanoflows here, and there are different kind of structure here, and then here nanodots are there. This is nanorods, and nano capsule shaped materials, and this is nanospheres and some other type of structure. Okay, so in the literature, if you go, people would often say nanoflower, capsules, polyflower, and so on, peripheral shaped nanomaterials, and so on. So these are some of the different images of the nanomaterials. And there are another class of nanostructured materials are also attracting much attention, and that is about core cell structure nanomaterials. And by carefully coating a shell material over a core material, and by changing the thickness of either this core or this shell material, their optical properties and then many other properties can be tuned to suit our applications. And these are some of the core cell structured nanomaterials which are prepared and reported in the literature. And nanorobots, and these nanorobots are very much useful in especially in medical industry, pharmaceutical industry, for delivering drugs. And if these nanorobots are given drug, and then they are controlled from outside, and then they will go through the blood, and then go and attach, go and release the drug in the area where the drug is to be released, and then so these tissues can be easily destructed. Okay, so you can kill virus and bacteria using these nanorobots, and then a very interesting study is that the application of nanomaterials in treating cancer. And in chemotherapy or radiotherapy, if you could give some radiations from outside, then this radiation not only kills the affected cells, but also kills the surrounding normal tissues and cells. And so therefore, but still those two are the very common treatment protocols available in the cancer patients. But targeted drug delivery is also being explored, and then there are many interesting reports in the literature which suggest that especially the magnetic material based nanomaterials are useful for the treatment of cancer using this particular thing, targeted drug delivery. And we sincerely believe that this someday in the immediate future, the benefits of this nanotechnology will be extended to the patients. And having said so much about the introduction about these nanomaterials, and then let me share with you some of the interesting results. This is about silver nanostructures and very simple experimental procedure is there. And actually in our university's synthesis of silver nanoparticles in different shapes. As I shared with you in my one of my slides, controlling the size and shape is very important in realizing the full potential of the nanomaterials. And this size and shape dependent properties of these nanomaterials can be very well utilized for a number of industrial applications, starting from pharmaceutical industry and healthcare industry and manufacturing industry. Everywhere we use these nanomaterials. And so therefore we thought, why not we take nanomaterial and then why not we synthesize these nanomaterials in different sizes and shapes. And we have succeeded to some extent, and we have done elaborate preliminary study to how to prepare this silver nanomaterials from different shaped silver nanomaterials. Okay, and this is a very simple synthetic procedure that we have adopted for the synthesis of silver nanomaterials. And while doing this experiment, we have also understood there are many other things are there by carefully controlling these parameters. Especially, you can take it from the precursor concentration, the pH of the solution, the temperature, reaction temperature, the reaction time, even order of mixing the reactants, and everything will affect the size and shape of the nanomaterials. And so, therefore, what we have done is we have kept all the other external parameters constant, but we have only changed the precursor concentration. By changing the precursor concentration and keeping all the external parameters constant, we thought we obtained silver nanomaterials in different sizes and shapes. But of course, you can get silver nanomaterials in different shapes and sizes by changing the other parameters also, especially by changing the pH of the solution also. You can get silver nanomaterials in different colors and in different shapes and sizes. You can change the reaction temperature, you can change the reaction time, and then the different cutting agents also you can change. And the surfactants concentration, by changing all these things, you can very judiciously prepare different shaped silver nanomaterials. And so here what we have taken is we have taken only silver nitrate solution, which is actually the precursor solution, and then we have taken sodium CMC and ascorbic acid, and then we have prepared solutions separately from silver nitrate, sodium CMC, and ascorbic acid, and then we have prepared these solutions in different beakers, and we have ensured that this material is completely dissolved in this solvent by continuously stirring each of them for about 15 minutes. And then to this silver nitrate solution, we have added this sodium CMC, and again we have stirred it for 15 minutes, and then after that this ascorbic acid is added. Then when this ascorbic acid is added, now we have seen the color changes. We have seen color changes. And we noticed that the color of the solution was slowly changing from pale yellow to deep yellow, and then as the stirring continues, then we got blackish green colloidal solution, and so therefore from this color change we could understand that this by introducing this ascorbic acid, this sodium ions are and reduced to sodium atoms. And this sodium CNC is a very good capping agent, and so therefore this sodium CNC selectively caps the different phases, and so therefore by controlling this sodium CNC and then the ascorbic acid, and then we could get nanoparticles. And then the nanoparticles, again, they are centrifuged at 10,000 RPM for about 10 minutes, and then we have removed only the dense products, and then this particles precipitates. And so again, it was to the deionized water number of times, and then acetone also several times, and then so we could take out this denser product, and then finally we tried this denser product at about 60 degrees Celsius for about 1 hour in hot air oven, and then finally we could get this silver nanomaterials. And this is what we have done initially to just to understand how this, whether these different shaped nanomaterials are obtained. And this UV simple spectroscopy technique is a very, very simple spectroscopy technique just to understand, to get some idea about how the size and shape distribution of the silver nanoparticles. So therefore, what we have done, we have taken this silver nanoparticles, and then we have recorded UV simple spectrum. And when the solution, which is prepared with the 0.01 mole precursor concentration, was subjected to this UV spectral analysis, and we could get SPR peak, surface plasma electron peak, at 437 nanometer. And if you look at this, peak, SPR peak, and then somewhat compared to other peaks, you can say this peak is somewhat symmetrical, and so therefore we understood that maybe silver nanoparticles would have been formed with a more narrow size distribution. But when the same silver nano, when the same, when the precursor concentration is changed to 0.02 mole, then this the peak at 437 nanometer is slightly blue shifted and stationed at 418 nanometer, and then we got also a solar peak at about 582 nanometer, and so therefore from this we have understood maybe we could have got a spherical silver nanoparticles, but then along with these spherical shaped silver nanoparticles, we also got an understanding that maybe some other shaped silver nanoparticles may also have been formed in the colloidal solution. And then the precursor concentration is increased to about 0.03 mole. Then the main peak, which was originally at 437 nanometer, was actually suppressed, and then and there was a slight shorter peak at 480 nanometer. But then there was a very prominent peak at 481 nanometer, which is higher in density, and so therefore we thought, okay, so this 0.0103 mole precursor concentration may have formed, more different shaped particles, nanoparticles. And when the precursor concentration is changed to 0.04 mole, then you got two peaks, one at 427 nanometer, and another peak of almost the same intensity at 540 nanometer. And so therefore, we got some idea that by changing this precursor concentration to 0.04 mole, then we would have got some other different shaped particles. So by doing the synthesis process itself, by looking at the color change, and then we could understand that silver nanoparticles are formed. But then before we analyze the colloidal dispersion for their size and shape using expensive techniques like TAM and then SEM, this is a relatively cheap technology, spectroscopy technique, and so therefore we have taken this spectral analysis, and then we got some idea that we have in fact produced silver nanoparticles in different shapes and different sizes. So this is a very beautiful spectroscopic diagram spectrum, which shows that this the SPR, the peaks of silver nanoparticles, and then their peaks are shifting. And normally, literature says that if with the increase in size, the SPR peak will be redshifted. So towards this 800 nanometer range, this peak will be shifted, and this is what we have obtained in our cells also. And then we wanted to understand the structure of these silver nanoparticles, and so therefore, after the CPB civil spectroscopy studies, and then we wanted to understand whether the silver nanoparticles are, I mean, they are the FCC first under the active structure of nanoparticles, but then we wanted to further confirm the structure of these nanomaterials, and so therefore. Now we have taken power X-ray as diffractogram of these silver nanoparticles in different mole concentration, and this is the X-ray spectrum of a silver nanoparticle, which are prepared at a 0.01 mole concentration, and then this one and this one and this one are the XRD spectra of silver nanoparticles prepared at different precursor concentration. Of 0.02 mole, 0.03 mole, and then 0.04 mole respectively. And we got in all these different precursor concentration, we got 3 peaks, one triple one, and 2 0 0 and 2 to 0, and these are the characteristic peaks of the silver. And we have converted this characteristic peak with the JCPDS part number, and we have confirmed that this particular product that we have synthesized is crystallized in FCC structure. And we have also studied the size, grain size using the CD/Schur formula, and when this precursor concentration is increased, actually, the D/Schur formula gave different grain sizes. So that is when the nanometer is prepared at a 0.01 mole concentration, crystalline sub 16 nanometer size is formed, which is very much consistent with the SEM and TEM results. And then when the precursor concentration is increased from 0.01 mole to 0.04 mole, slowly the crystalline size slowly increases from 16 nanometer to 22 nanometer. Not much change in the crystalline size, but then these are ample evidences that this different size nanoparticles are formed. Then after this port X-ray studies, then we have recorded this SEM, scanning electron microscope images of this silver nanoparticles prepared at a different precursor concentration. So if you look at this first image, then you can see this silver nano spheres, more or less, spherical shape. Some agglomeration is there, but then mostly this silver nanoparticles formed here are spherical in shape. But then when slowly this precursor concentration is slowly changed to some 0.02 mole, then along with this spherical shaped nanoparticles, you can see here and there some small capsule and rod shaped nanoparticles also embedded inside these silver spheres. But once again, there is still agglomeration, but then different shaped nanoparticles are formed. And then when this again is 0.02 nanometer, mole concentration, and when the mole concentration is increased to about some 0.03 mole, then slowly this spherical shaped nanoparticles, more and more spherical shaped nanoparticles are getting transformed themselves into different shaped particles, and not completely they are changed into different shaped particles. But then you could see very clearly from here that these nanomaterials are no longer completely spherical. But then small spherical shaped nanoparticles are also there, but then predominantly this image is predominated by different shaped particles. Interestingly, when the precursor concentration is changed to about 0.04 mole, then very interesting results we got. We got some prismatic shapes, and here is one prism, nanoprism, which is very clearly formed here. And then these are maybe they are also prisms, nanoprisms, but then these nanoprisms are oriented in different directions. And maybe that is the reason why you are not able to see these prisms very clearly. But then this is a very good proof that the silver nanospheres, silver nanoprisms are beautifully formed when the precursor concentration is increased to about 0.04 mole. So therefore, when the precursor concentration is changed from 0.01 mole to 0.04 mole, then when we calculated the size, we also saw some size distribution, some 31 nanometer to 40 nanometer, and then the precursor concentration is changed to about some 0.04 mole. Then silver nanospheres in different shapes, different sizes. Some nanospheres are also there, but then they are not dispersed here and there with their sizes ranging from some 20 nanometer to 200 nanometer. There are small, very small shapes. Crystals are also embedded inside the image. The very fact that the small nanospheres are still there, you can safely say these silver nanospheres are combined together, and then and because of the action of the sodium CMC and ascorbic acid, and the growth of these nanostructures in different phases are affected by this sodium CMC especially, and so therefore differentiated nanoparticles are timed. And this is the sun image, and then we have also taken the CLX image, and then from the CLX image, you got only the peaks characteristics of silver, and the very fact that you have no peaks of other elements, you can safely say that this material that you have prepared is only silver material. And we have also recorded this term images, and then just to confirm our studies. And though some images gave a sample evidence that different shape and different morphology particles are formed, but then we also wanted to take the term images, and then we wanted to see. And if you look at this, this is the image that is recorded for the silver nanomaterials prepared at precursor concentration at 0.01 mole. If you look at this, and you see some different spheres, mostly spheres, and then almost equally spaced spheres. No, boundaries are well separated, and then and they are formed almost in similar particle size range. Though there are here and there particles with different higher sizes, but then most of the particles are formed in spherical shapes, and that is the reason why in the SPR peak also is showing sharp peak at 437 nanometer. And this is the sun. This is the time image that is recorded for the silver nanoparticles prepared at the precursor concentration, which is 0.02 mole. And if you look at this, you see spherical shaped nanoparticles, but then the spherical shaped nanoparticles are also along with these spherical shaped nanoparticles, you see some rod shaped nanoparticles, and then capsules, and then slowly the size is changing to the shape is changing to different shape, and though again here spherical nanoparticles are there, but then slowly the size is shape is changing. And if you look at this, the precursor silver nanoparticles formed at the precursor concentration is 0.03 mole, you could get the silver nanoparticles of different sizes. Here, the size distribution is different. Very small spheres are there. In addition to the spheres, you can see these prisms. You can see prisms, and then some rods, some small capsules, and so on, and so on. And this is the term image recorded for silver nanoparticles prepared at 0.04 mole concentration. Here, just in confirmation study, especially as it is seen in the some images. Here also you see the different prisms, but then the prisms are oriented in different directions, but then most of them are spheres. Okay, so therefore you can say that by controlling this precursor concentration, by controlling the experimental conditions, and you will be able to synthesize the cellular nanoparticles in different shapes and sizes. And these are the images which are put in one slide, and then for the particles prepared at different precursor concentrations. And this is also the SIAD image, and I mean this very much confirms with the structural study that is done by our X-ray reflections. And this is a simple table which shows that we have counted actually in the images we have counted, and when the precursor concentration was 0.01 mole, mostly spheres are formed, but then there are nanorods are there, but then persons are not there. But then when the precursor concentration is changed to 0.02 mole, then the spheres, number of spheres reduced, and then but the nanorods keep increasing. And when the precursor concentration is increased to 0.03 mole, the spheres is down to some 32, and then there are nanorods shaped structures we have seen, and then we could also see triangular prisms. But then when the precursor concentration is changed to 0.04 mole, then mainly the triangular prisms, in addition to small shaped spheres and triangular prisms are also found. But then what we have done is by simply changing the precursor concentration, but then maybe yes, there is slight changes in other experimental parameters also causes some instability, and so therefore we have not completely controlled the size and shape of the silver nanoparticles. But then by changing this precursor concentration, we have demonstrated that these silver nanospheres can be grown into silver nanoprisms. So that is what is our findings. And so therefore, just to conclude, we have synthesized and nanosized silver nanoparticles in different shapes and different sizes using a simple chemical detection method, and then we have characterized these silver materials using different characterization techniques like some, UV-visible spectroscopy analysis, and then polar X-ray diffraction studies, and then to see their sizes. We have also collected some images, and then so therefore we conclude that this by changing the precursor concentration, we can know by controlling the experimental parameters very carefully, we can switch spherical shaped silver nanoparticles to different shaped nanoparticles, some rods, some nanoprisms, and so on. And so I would like to thank my research scholars for doing this small work on silver nanoparticles. For us, this work actually gave us some understanding about some basics of silver nanomaterials. And though we have got some references in the literature which says by controlling the various parameters, judiciously you can obtain nanomaterials of any particles in different shapes and sizes, and by tailoring this size and shape, you can actually tailor the optical properties and other properties of the nanomaterials. And so therefore, we conclude that by by controlling this precursor concentration, we can get silver nanoparticles in different shapes. Thank you.
Thank you, sir. Yes, it's time to clarify your queries. Dear participants, those who have any questions, kindly raise your queries. Kindly unmute your mic and raise your queries. If you have any questions, kindly raise.
Yes, sir. This is Rajeshwari from Hindustan Institute, sir. Dr. Jose, sir, your presentations was very nice. And my doubt is why we always choose a silver material Is it has any bio applications further from this? Can you say the importance of it? Because silver is usually a costlier material. So how we have to go with the silver structures?
Thank you for asking such a beautiful question. In fact, I failed to decide on the applications of the silver nanomaterials. And mainly these silver nanomaterials are used in the medical field. But of course, they are also used in the sensing and the biosensing for the sensing different things. But mainly this silver nanoparticles and gold materials are used for antibacterial applications. And that is the reason why nowadays if you get some ointment for applying to the wounds, if you could read the thing, you will clearly see that some nanosized particles are incorporated in the medicine, in the ointment. So if nanosized silver nanoparticles are incorporated in the ointments, then the healing time will be reduced. The healing time will be reduced, and then this will also inhibit the growth of microbial agents on the wound. So therefore, people are using this silver nanoparticles for antibacterial applications, especially in wound healing. And that is one of the very interesting applications of the silver nanomaterials. But then silver nanomaterials, has to be prepared using either silver chloride or silver nitrate because of. But then, as you said, silver based products.
Thank you, sir.
For that matter, even the other materials.
One more question, sir.
Applications is not very nice in the medical field. So therefore, this cost. Maybe if you go for some larger scale products in silver particles or silver or silver chloride, maybe the cost will go down. And also this not just for wound healing, especially because of its antimicrobial applications, but then the silver nanoparticles are also very much useful in biosensing applications. And not just that, but then this silver nanoparticles, metal and the noble metals especially, and this silver nanoparticles and then gold nanoparticles are very much being tried in the medical field for targeted drug delivery and so on. This gold and nano silver, there are occurrences in the literature which says that these materials could be used in the targeted drug delivery applications, and the benefits of these materials will easily come into the market in the time in the near future.
Yeah, I can understand. So one more question regarding this. Usually when we prepare silver using this chemical reductions method or any wet chemical processes, they say the stability of the silver is lost. Either it turns to silver oxides or other form of a thing. Can you comment anything on the stability of this material, sir?
Yes. Once again, I would like to thank you once again for such a nice question. And in fact, we have added sodium CMC, and that is a stabilizing agent. And now if you don't add this stabilizing agent, then what happens is you can prepare this silver nanoparticles, but then when they are dispersed in the solution, and then slowly these nanoparticles will get attached to themselves, and they will get agglomerated very easily, and then these small size nanoparticles will grow into bigger size, and even maybe they will be converted to micro-sized particles as well. And so therefore, that is the reason why in the chemical reduction route, and people are using some stabilizing agent or capping agent. And here, many stabilizing agent and capping agent can be used, like PVA, polyvinyl chloride, and then PVP and other polymer-based capping agents also can be used. But then here, what we have done is sodium CMC we have used, and then this sodium CMC prevents this sodium and silver nanoparticles from getting agglomerated. And the collateral discussions that we have prepared using this Technology-NCIST was stable for a period of about 6 months. And we couldn't notice any noticeable color change in the collateral discussion. That shows yes, the silver nanoparticles prepared using this chemical reduction arrow is stable because of the use rate of this stabilizing agent like sodium.
Sir, one more question from chat box. Shivakumar, research scholar, can you clarify the physics relation between size and absorption of light?
Size and absorption.
Yes, size and absorption of light.
Okay. No, that I'll just show you. The different sized particles. No, this here in the case of silver nanoparticles, I said there is a surface plasmon resonance peak. This is the characteristics of the metal nanoparticles. Normally, silver nanoparticles will show SPR peak at 405 to 440 range, and other metal nanoparticles will show SPR surface resonance peak at different nanometer. Here, what is happening is the size actually is conduction electrons when they are in oscillation. When you pass some ultraviolet radiations, what happens is this ultraviolet radiations are observed at a particular wavelength. So these conduction electrons are oscillating at a particular frequency, and when you pass this ultraviolet radiations or visible radiation, what happens is that when the resonance of these two things matches, suddenly absorption is taking place, and so therefore that is what is product in this thing.
And one more question from chat box, sir. Bharat from University of Madras, how the surface tension of the solvent affects the crystallization of particles?
The surface tension, how surface tension affects?
How the surface tension of the solvent affects the crystallization of particles?
But I know this surface tension of the solution that can be affected by crystallization properties. But then, frankly speaking, I do not understand. I mean, I do not know exactly what role this particular surface tension is playing on the crystallization.
Okay, thank you, sir. On behalf of the participants, I would like to thank Dr. M. Jose for his indelible presentation. Your passion towards nanostructure and nanospheres always motivate us. The way you carry yourself is truly admirable. Your potential is limitless. We are grateful for the time and the effort you took to share your thoughts and experiences with anisotropic growth of silver nanostructures from silver spheres. I am sure that participants will get attracted by your knowledge and research experiences. Thank you, sir. Thank you so much for your spending a valuable time, sir. Thank you so much.
Thank you. Thank you. Thank you once again. Thank you, the organizers, in a very special way. I would like to thank once again the convener of this conference, Dr. Saranraj, for inviting me to give a talk for this conference. Thank you once again.
Sir, thank you, sir. Thank you so much.
It was a delightful experience in listening to Dr. M. Jose. Thank you, sir. On behalf of the organizing committee, we are very much grateful to the chairperson, Dr. J. Tirupati, for his effective contribution. Thank you, sir. Ladies and gentlemen, let's break for refreshment, and you are requested to gather in the same link for the next technical section at 12:30 p.m. The following slot numbers N201, N204, N207, NT10 and NT55 for oral presentation are asked to report the same link at 11:45 a.m. A gentle reminder for the selected slot numbers, you are asked to send your PPT to the organizing committee. Thank you.
Thank you, Surendra sir. Thank you, Manivanan sir.
Thank you, ma'am. Thank you, ma'am.
Thank you. Later we will start by at 11:45 or 12.
11:45, ma'am. That is a oral presentation will be started.
Okay, sir.
Then go for 12:30 is the next section, ma'am.
Okay, sir. Thank you, sir. Thank
Okay,
you for
thank
all.
you.
Thank you very much.
Madam, we can leave the meeting.
No, ma'am. This is a continuous same schedule. Okay, just 5 minutes, just for refreshment only. Okay.
Oh.
After 11:45, as the oral presentation started here.
Okay.
Dear participants, please share your PPT through conference email. NT01, I got it your PPT. So NT10, the 2 PPT I got it. So remaining person, please share your PPT through email.
Sir, can we share our screen by ourselves or?
Because of that is not possible, ma'am. The host only share the screen. Okay, please you share the PPT. Send it to your PPT, ma'am, through email.
Yeah, I have sent.
Okay.
Sir, I had shared my hello.
Sir, tell me, sir.
Hello. Yes,
Yeah,
I have shared my PPT with you. Actually, there is one.
01.
I mean, yes, sir.
Yeah,
In
I got
slide number 4. Yes, sir. In slide number 4, there's a video of 20 seconds.
Okay.
If you can see that.
Just a minute, sir.
In slide number, yeah, you just play that. I mean, if not, then I mean you continue. I mean, but just wait there for some 20 seconds. I want to explain that.
Just
in
I
slide
share.
number 3.
Okay, sir. Now I share this screen your PPT, sir. Just play or not verify that.
Okay, sure.
Okay.
Yeah.
I hope you can visible your slide.
And yes, sir. Sharing full. Yes, sir. Yeah. This only.
Yeah, it's not placed, sir.
Sir.
Okay.
No, if you play, put in sir full screen mode. No, not like this, sir. That. No. Yeah, this one. Yeah. Now go. Now you move. Now one more. Now click on that. Down. No. On that. No. Back, sir. No, back. Yeah, down. You can click there also. Yeah. Click there, sir.
No, sir.
You just click.
Yeah, I clicked that one.
Oh, okay. Okay, it's okay, sir. No problem. There's no problem. It's okay.
Thank you, sir.
Or if it is possible, like, can I share like my PPT from my own side, if you permit me?
Yes, sir. I will accept your request. Okay.
Thank you, sir.
Now I put it for your name is a co-host. Okay.
Thank you so much, sir. Thanks a lot.
Okay. So, dear participants, don't ask the same reason. Okay. Please share, send it to your PPT as soon as possible.
It is 10:45, sir.
Welcome back everyone. It's time for oral presentation. The slot numbers for oral presentation are as follows: NT01, NT04, NT07, NT10 and NT55. The judges for the oral presentation are Dr. M. Manivannan, Dr. J. Tirupati. I request the judges to take over.
Dear participants, am I audible? One of you?
Yes, sir.
Yes, sir. It's audible. You can continue.
Your presentation time is you can take 10 minutes for your presentation and 2 minutes for discussion. Please be on time to finish. Okay?
Okay, sir.
Yes, carry on.
Good morning, everyone. I am Mohammad Azaddin Ganai, IIT Madras. I work under the supervision of Professor 01. The title of my talk is Electrospray Nanofiber Mats as Smart Surfaces for Desorption Electrospray Ionization Mass Spectrometry, DCMS based analysis and imprint imaging. As part of introduction, ambient ionization mass spectrometry, in particular, desorption electrospray ionization mass spectrometry, DCMS, requires flat, rigid surfaces for capturing molecular signatures faithfully. They have to be registered and then revealed without losing spatial information. Surfaces reported for ambient ionization mass spectrometry include PTFE, TLC plates, porous silicon, nanoporous alumina, but they have certain limitations. In this work, DESI-based molecular analysis and imprint imaging using electrospun nylon 6 nanofiber mats are demonstrated for various analytical contexts. Analytical applications requiring rapid understanding of the analytes in single drops, dyes, inks, plant extracts incorporated directly into the nanofibers are discussed with illustrations and examples. And the possibility to imprint patterns made of inks, plant pots like petals, slices of rhizomes, and fungal growth on fruits with their faithful reproduction on the nanofiber mats is illustrated with suitable examples. So, what is mass spectrometry? I mean, we know it's an technique by which we determine the mass of species, compounds. Okay, there are 5 main parts of mass. One second. There are 5 main parts of mass spectrometer: sample, inlet, source, analyzer, detector, and data output. And then one such, there are different types of mass spectrometers. One is DESI-MS mass spectrometer. So it actually does mass characterization of the samples under ambient or atmospheric conditions. Now, what it gives, like there are 2 things like which we can obtain from this mass spectrum. One is like this the mass spectrum of our sample, and one more thing which we can obtain in the imaging. We can do the imaging of the samples with this DCMS mass spectrometer. Here you can see different, I mean, species like we have the cells which are have been got affected with cancer, and we have done 3D molecular imaging, drug mapping, and many other things have been imaged with this mass spectrometer. Now our many modifications have been done in this mass spectrometer to get good resolution and good imaging. And in our case, what we have chosen, like we can play with this detector, we can play with this capillary or voltage or many such things. And the more interest in our work is this sample stage. As I mentioned, many like sample stages have been used like TLC, PTFE, that they have issues, like the issues they are having, like they are having porosity, or they can do some catalytic activity with the species, or they can do some other things which can photochemical degradation. But we are looking for a material which can overcome these things. So for that we have used electrospun nanofibers, and electrospun nanofibers are having, like they are having porosity, they are having good large surface area, and they are chemically inert mostly, and they do not interfere with the nature of the compounds of our interest. So for electrospinning, we have to use a setup which is electrospinning setup. Usually you might have seen a conventional electrosetup where we have like syringe connected with high voltage setup, and then electrospinning is needleless electrospinning setup. And in that, what we do, we take our solution here in a like bathtub, and then here is our collector. Okay, and with this setup, actually we can draw big sheets of, I mean, matters with electrospinning, and the time taken by this process is very less compared to a conventional electrospinning setup. The conventional electrospinning needle-based electrospinning setup in some 12 hours that we can do within some few minutes only. So this is the good property with this needle-less electrospinning setup. And we know there are a lot of solar cells and tissue engineering. So I mean, these things also can play an important role, because most of things we have to deal with electrospinning, with DESI, with mass spectro analysis and also imaging also. And then the setup that I was mentioning is here. You can see, I don't know whether I will believe. Okay, leave it. So this is our electrospinning setup. Here you can see this is the tub where we are taking our solution. This is the electrode, and this is the collector. Okay, you can see a white patch of nanofibers getting formed on that. And then after doing our experiment, these are the results. I mean, these are electrospinning. Like when we do electrospinning of any polymer, then we will, I mean, do the SEM and see how good images are coming. I mean, there should not be beads, and there should not be this good and clear nanofiber images should be coming. So you can see here we have got very clear and without any spines or any beads, we have got clear these nanofiber mats with uniform diameters, and we have varied the thicknesses of these mats. You can see here almost 50 micrometer thickness mat has been produced here, almost 100 micrometer and almost 150-160 micrometer mats have been produced for our various experiments. Now, what we have done actually, as I mentioned, we have used these mats for various analytical contexts in our mass spectrometry. So first thing which we did actually was like we have taken methyl orange, a drop of methyl orange, and we have drop casted it on our nanofibrous mat, and you can see how uniformly it is spread. But when we take the same, drop on TLC, you can see how it is spread, and in between, like there's a halo formation where we can see it is going to the surfaces, and between it is coming not coming clear. And when we do, we got a very clear, mass spectrum with very low noise when we did on our nanofiber surface. And you can see here, like it is not coming in good. And also we have taken periwinkle flower extract also. Here also we have characterized it. But when we took the same on the TLC plate, you can see how it is getting spread out, and also with after some time it will lose its color, and that's the problem with normal TLC plate. Okay, and basic imaging when we did on fibrous mat, and it is on TLC, and you can see the spectrum also how much noise is coming. Okay, so from here we can see that our material is comparatively better than a conventional TLC surface. And one more thing with our material, when we are doing the electrospinning, we can take some extracts and we can mix directly them with the polymer solution when we are making the polymer solution or electrospinning. So we have done that with the periwinkle leaf extract. We did take the extract and we mix with nylon polymer solution. We have make solution of that. Then we have electrospin. This is the fibrous mat that we got. And then when we have done the characterization, we have got almost all the features corresponding to the periwinkle leaf extract, and we have done imaging also, and where we have seen a uniform distribution of the various metabolites which are present in the periwinkle flower extract. And further thing, actually, one more thing that we can do with our material, nanofibrous mat in this imaging, we can study the effect of spraying or wetting of the sample. So what is that means? Like if you take this is actually turmeric paste that we have put on our nanofibrous mat. Actually, when we take a solution of methanol and water from in capillary, so we know like water dissolves some of the parts of turmeric. Okay, so we are expecting a change in spectrum after wetting. Okay, this is actually fresh surface has been taken. We have taken mass spectrum, and after wetting we have seen the spectrum is coming. But we have seen even after wetting the imprint is not damaged on a nylon fiber mat. So we can see
Go to conclusion.
are coming from the the pattern that is happening. Yes, when we did the same thing on a paper, you can see like it is getting distorted, and we are not able to do this study. And further, we can do good imprinting of patterns. You can see we have written nylon, and we have taken some with mark, and we have done it with a printing pen we have done, and we have got very clear images with no overlapping on nanofibrous mat. But we do the same on this. And similarly, we have done imaging of various plant pots, and we have very clear images. But for TLC plate, you can see after some time it is getting invisible, and also we are not getting good this image. And further, we have been able to image this last slide, sir. This last slide, we have been able to do. If an infection or disease on a fruit, we can detect that also. And here we have seen a fungal growth on lemon, and we have detected the toxin which is present there. So these are the different metabolites present that we have detected, and we have obtained them from the database and literature. So coming to the conclusion, we have seen that the stability of nylon nanofiber mats as smart surface for Desi MS using examples including patterns made by single drops and with dissolved dyes, marker pens, inks, and printing inks. No overlapped images were produced from imprinted patterns on nanofiber mats made of inks, however close they may be. Imprint of plants demonstrate the significance of nanofiber methods, smart surface for identifying and preserving diverse sources of compounds, and we can image the fungal and other infectional contamination growing on fruits. And this result suggests that these electrospin nanofibers can be made industrially. Their use in DCMS can become a promising method of analysis. So these are some of the references. And for this, I am thankful to IIT Madras and DST for funding research group, my research lab, and SVCT for giving an opportunity to present my work in this conference. Thank you for your attention.
Nice presentation. Dear participants, can you ask any questions? Please raise. Dear participants, if you have any doubts, you can ask, please. Okay, Mohammed Asaruddin.
Yes, sir.
And you can use some electrospray droplets, right?
Not electrospray droplet. Actually, this, I mean, when we are in DCMs, actually, this spray will come out. That droplet. But for this mat, we are using nanofibrous mat.
Please go to the experimental slide.
This one, sir.
Back. Here you can mention the electrospray droplets, right? Go to second.
Yes, sir. Yes, sir.
Yes, this one. Can you measure the droplets of the diameter?
I mean, there are some micro droplets, and as such, I mean, measuring them, I'm not sure, because it depends on the voltage. The more high voltage we use, and like, this less will be their dimension. So usually we are saying that their dimension is in micrometers.
Micrometer, okay. You can take the single drop. How much in quantity you can measure? You can use the single drop. Next slide, go to next slide. For analysis purpose, you can take a single drop, right?
Yes, sir, which is there, yes. Yeah, it is actually, that is separate, sir, actually. That is our sample here. It is not, I mean, that thing. It is our sample on this one. This is separate, actually. This droplet is a charged, droplet, which is, you can see it's a high voltage power supply. I didn't explain it in detail, so we will use some solvent. Usually in our experiment we are using methanol. Okay, so when it is connected with this high voltage supply and it is coming through this, this capillary, so they are charged. So from this surface they actually dissolve some of the molecules from this sample, and it goes to the detector. We know because this mass spectrometer only detects this ions, either positive or negative. So for that we have to charge the surface of this sample. So that is why we are using these charged droplets to come out our surface. It is here actually we are taking one droplet, one drop of this methyl orange.
Okay, and
here,
go to next.
Actually, yes.
You can use some turmeric paste.
Sorry, sir.
Yes, you can use in this slide. You can use turmeric paste. You can say that turmeric paste.
Yes, that is, it is here, sir. Actually, it is not actually paste. It is actually, we have taken an imprint of that. So we have made it on some step, that we have made just imprint. It is not full paste. We can take paste also, but the less amount of sample, because we take, it is good actually. The less amount of sample for characterization, it's good for any characterization.
How you conclude that this turmeric paste is working in your sample?
Yeah, actually, sir, you can see when we are taking turmeric on our sample, it is not, the image is not deformed. But when we take, you can see here, like we have made, this is a drawing actually we have made of turmeric paste. But when we do, when we put spray on, it is on actually paper, printing paper. You can see like what happens after spraying. But with this case, it was, getting attached. It is having porous structures and nanofibers, and also it is
Okay. Thank you. Thank you
It
so
is not
much.
Yes.
alone, I mean,
Okay.
get deformed. Okay.
Okay.
Thank you, sir.
So nice,
Nice
sir.
question.
One more question from the audience.
Yes, sir.
Mr. Shiva asked, what is the social relevance of this research works?
Sir, social relevance is like, as I said, that mass spectrum, you can see like mass spectrometer is one of the, I mean, unique technique because it gives us the exact details of any molecule or any compound. Okay. And many things are now getting changed with time. Like it is not on spectrum, we are able to do the mass imaging also of samples. You can see like many drug imaging, cancer disease and all those things. Tumors have been also diagnosed with this, I mean, setup. Now, the more better resolution and good imaging we get, that is more helpful. Okay, so that is why in this context we have taken this, I mean, sample stage, and with our material we are comparatively getting better results than the conventional surfaces. So in that aspect, we are seeing that we are, I mean, bridging that gap where we are able to get good spatial resolution and also good imaging with our material in mass spectrometer. So obviously we will get them, these characterization will be more fruitful and much better with our material.
Okay. Thank you.
Fine, sir. Thank you.
Thank you,
Next,
sir. Thank you.
NT.
Yes. Now I invite ND10.
Is my voice is audible, sir?
Yeah, it's fine, ma'am. And before you're starting, ma'am, there is a small announcement for the audience. If any of the audience is ready to present the presentation or ask to send your presentation to the conference mail ID so that you can able to present. If there is availability of audience of NT04 and NT07 and NT55, immediately send your presentation to the conference mail ID so that you can able to present your presentations. Sorry for the inconvenience, man. You can start now.
Okay. A very good morning to one and all. I am Dr. N. Rajeshwari Yogamalla, Assistant Professor in the Department of Physics, Hindustan Institute of Technology and Science. Today my presentations is on, so screen is not visible.
Just a second, man. Is it now okay, ma'am?
Yes.
Yeah.
Can you go to the next slide?
Yes.
Okay. So my presentation is on indium incorporated silver sulfide as light sensitizer in a photovoltaic cell. So, as per the current scenario, non-renewable energy sources are continuously utilized by the thing to produce the electricity. So in the near future, we are going to exhaust these non-renewable energy sources as we are rising with the populations and we are over-consuming it. So researchers now focus mainly on the renewable energy sources for electricity production, and as a credit, in the past 30 years, nearly 10% of increase in the energy consumption is effectively achieved with the solar and the wind energy. Can you move to the next slide, sir? Next. Yeah. So again, next slide, sir. So to meet the global crisis, it is essential to look for a new material. So I just used a functionalized zinc oxide, which is incorporated with the light sensitizer silver sulfide, along with the conducting material indium. And this motivated, and to meet the global crisis, this material will be a futuristic scope for everybody. So next slide. So the major requirements and updation which are required in previous slide, which are required in photo energy conversions are put under three heads: the efficiency, lifetime, and cost. Efficiency stands for the output, maximum output energy, what we get with respect to the input energy, and lifetime tells how long the device can work so that the stability of the material can be encountered. And finally, it is nothing but the cost. It should be available easily, and it should be non-toxic, environmentally friendly, and it should meet all the social, demands met with the societal needs. Next slide. Okay, so in my research, first I have chosen silver sulfide as light sensitizer. You know the role of light sensitizer. It should have a maximum light absorption, which covers the entire electromagnetic spectrum range, ranging from the ultraviolet visible to the near infrared region. And silver sulfide, moreover, crystallizes in a monoclinic phase. It has a band gap of 1 to 2 electron volt. So energy level band gapping can be tuned very easily. So it matches with the conduction band edge, that is the absorption edges of the material and counter electrode. And finally, silver sulfide can easily adhere with any contact surfaces. So this promotes the long life for the excited electron. So it reduces the recombinations rate, which is a main criteria for photovoltaic conversions. Next slide, please. So along with the silver sulfide, we also choose indium as a metal dopant. Why we have to choose? Because indium has a very high ionic conductivity of 10⁻⁷ Siemens per meter inverse. Such a conductivity can promote the fast movement of the charge carriers between the counter electrode. So the current can increase and efficiency can also increase. Second, it is being an additive or a hybrid material, more number of electrons are injected into the conduction band, and finally this again reduces the recombinations rate. So that's why it is used. And last, it has a cationic size of 156 picometer, which is much higher than the other host atom present in the material. So again, being with the higher sizes, the current efficiency will be increasing, so the maximum output can be gained with the help of this indium ion. Next slide, please. So this is my methodology. So I just in my experiment used a wet chemical hydrothermal process to synthesize the pure zinc oxide, silver sulfide and indium incorporated silver sulfide, and both are put under a nano composite. So to synthesize zinc oxide, which is represented as the letter capital Z, zinc nitrate and sodium hydroxides are used as the precursor, and it is the mixture which we got as a milky white solution. It is put in the hot air oven at 90 degrees Celsius for 6 hours. In the synthesis of silver sulfide, silver nitrate and sulfur are used as the precursor. Both the samples are initially stood at a separate sample, and then they are mixed together and maintained at 120 degrees Celsius for 8 hours in hot air oven. A black precipitate was obtained. It was washed repeatedly and then dried out. The same procedure was also adopted for indium incorporated silver sulfide, which is represented as AAS. The one step what we have done is indium precursor, which is a 0.4 millimolar of indium acetate was added to the solution. So now we have the two solutions. Both were made as a nano composite, zinc oxides along with the pure silver sulfide and indium incorporated silver sulfide. The ratio what we have taken is 4:1. Next slide, sir. So this shows the photographic view of the pure zinc oxide, silver sulfide, indium incorporated silver sulfide, and the last two is the nano composite. So you can see the color variations in both the nano composites. It's mainly due to the incorporations of the indium ion. Next slide. So throughout our experiment, these are the basic materials and the tools we use for the synthesis as well as characterizations to confirm the material formations and the product results. Next slide. This shows the basic characterizations, the X-ray diffraction. The first plot shows the pure X-ray diffractions or the zinc oxide, which is, crystallizes in the Hood's-eye hexagonal form. And using Scherer equations, we were able to get the average crystalline size of 37 nanometer. The second plot shows the pure silver sulfide, and the third shows the indium incorporated silver sulfide. If you see the silver sulfide and indium incorporated silver sulfide, we have obtained the same XRD diffraction pattern, and the peaks were indexed with the same, the JCPD is 893840, and it crystallizes in the monoclinic crystalline phases of silver sulfide. This clearly shows that indium is well occupying the silver sites. So as I said earlier, the indium has a high cationic sizes compared to the silver ion. So my peaks are shifted towards a redshift, that is the higher angle, and the lattice is strained tensilely. Next slide. This is the XRD pattern for my nanocomposites. If you see the ZAS and the SADIS, the ZAS has only the hexagonal phase of zinc oxides and the monoclinic phase of the silver sulfide. Whereas in the case of indium incorporated silver sulfide, along with the hexagonal and the monoclinic phase, a tertiary impurity phase because of indium sulfide was also present in our material. So this is because mainly the activation's energy, when we start adding one material with the other, the rate of dissolubility, the solubility differs, and the activation energy for indium is much higher. So it starts to precipitate earlier when compared with the silver sulfide and zinc oxide. So that is the reason for the tertiary phase present in my material. Next slide. And this shows the same micrographs of the pure zinc oxide, silver sulfide, and indium incorporated. If you see the sample of zinc oxides, you can see a flower-like arrangement. You can see the petals have been drawn. All these petals are in different dimensions ranging from 400 to 720 nanometer. This is mainly because of the capping molecule polyethylene glycol present in the material results in the anisotropic group. Whereas in silver sulfide and silver indium sulfide, we all know the silver is mainly for a nano-sized particle confinement. So because of large surface area and reduced particle size, more number of particles come closer to each other and results in agglomerations and aggregation. Next slide.
Ma'am, time is over. Go to the conclusion.
Please, first you are delayed now. I'll just take 2 more minutes. Yeah. So this is the composites form. You can see the rods as well as the particles. The rods are evolved from the zinc oxides and the particles are from silver sulfide and indium incorporated silver sulfide. So we can say the petal-like, flower-like arrangement of zinc has evolved to a rod shape and the particles are well adhered to the surface of the rod. Next slide. And this is the optical spectrum. You can see the absorption spectrum, which is shown in the second plot. The silver sulfide and the indium incorporated silver sulfide in this nanocomposite shows a broad range of absorptions ranging from 300 to 1200 nanometer. This shows the maximum light absorptions from the UV, visible, and the IR region can be incorporated for photon absorptions and excitation process. Next slide. This shows the complete device what we have formed, the PN junction, the photovoltaic cells, IT-volt coated glass substrate, the nanocomposites acts as the N-type material, the semiconductor rose bengal act as a P-type material, and the top we have the counter electrode gold. So as we prepare these materials by the wet chemical processes, the individual layer is not visible. So the overall thickness of the layer what we have made is of 120 micrometer. Next slide, please. So this shows the working. You can very clearly see when a photon of energy H2 falls, as the P and N junctions have a very good energy matching between them, the electrons and the presence in the valence band can be easily shifted to the conduction band and take part in conducting. And that enriches the photovoltaic conversion. Next slide. So this was the efficiency when we have measured with the PN junction. So the top sample shows the nanocomposites with the pure silver sulfide. So where we have attained the efficiency of 0.76, when indium was incorporated in it, we were able to have a 1.2% of efficiency. And moreover, the voltage, the open window voltage is also shifted to 0.62 volt in the case of indium incorporator silver sulfide. So this shows that indium plays a major role in enhancing the efficiency of photovoltaic cell. Next slide. So my overall conclusions, I just adopted the wet chemical simple process to synthesize my material. The sample silver sulfide and indium incorporated are nanosites, and it has a very good contact resistance between the PN junction. And finally, when indium was incorporated, which has a high conductivity and high cationic efficiency, size, it improved the efficiency to 1.2%, but still it is a lower. When we adopt an optimized synthesis method, we can definitely improve this value to a higher value. Thank you all. Yes, sir. Thank you.
Thank you, ma'am, for your nice presentations.
Thank you, sir.
It's time for the audience to raise your questions. So audience, if you have any doubts, you can clarify now.
Ma'am, I have a question.
Yes, sir, please.
In this slide, you can tell the solar efficiency of 1.2%. It will be improved when comparing. Which one you can compare?
Right now, the efficiency of the peroxide solar cells, they have attained to be 26%. Okay, so when compared to 26%, my 1.2% is a very smaller value. But the role the indium play, okay, now we mainly look for graphene molecules as well as carbon allotropes molecules. So my role is these carbon molecules can also be replaced with the indium. So the same material, if I make it in a peroxide material, I can again have a higher efficiency. So that is my idea. What I say is
Actual color for
I can't hear. What's your
the
question?
actual color of indium?
Indium is a brick red color, so.
And what is the texture?
Texture. Yeah, indium acetate we were using. So when the indium ion is incorporated, it's usually in a solubility. It's a solvent. So it's like a liquid format.
Okay, thank you, ma'am. Thank you for your presentation.
Thank you.
Just a second, ma'am. We have a question from the audience side.
Raise one question, ma'am. All materials are not having transparent, invisible region. How it can be potential materials, electronic and energy conversion applications?
It was very clearly shown the reflectance as well as the absorption spectra, because we have to absorb the maximum sunlight energy. Okay, so my absorption should lie in UV, visible as well as IR region, because IR region has the maximum conversion efficiency. When you see my sample, the silver sulfide and the silver indium sulfide, it shows a range of visible range. You can see because zinc oxides comes in the UV as well as visible. If you go to the slide, sir.
Yes, ma'am.
So the transparency is maintained. Absorption rate has been increased. Yeah, can you see? The top one is the reflectance spectrum. So this is for pure silver sulfide and thing. You have only infrared range. But when you put it in the nano composites, you can have the range comprising from 330 nanometer to 1200. That is, it has a range of UV, visible, as well as the infrared region. So this is very essential for photovoltaic conversion. So I to achieve the same, the optical properties.
Okay, thank you, ma'am.
Yes, sir. Thank you.
Thank you, ma'am, for your nice presentation. It's an open option for the audience. If anybody is willing to present your presentation, you can present now. Kindly share your PPT through your conference mail ID. If not, we will continue the next section. It's now I hand over the section to the organizing committee for the next sections.
Excuse me, sir.
Yes, tell me.
Am I audible?
Yeah, come again.
Am I audible?
Yeah, you are audible.
Shall I present my screen, sir?
What's your slot number, ma'am?
55.
55. Just a minute. Sir, not received. Your PPT is not received, ma'am.
I will do my PPT myself, sir.
Conference mail. Could you send to the conference mail ID, ma'am?
Pardon, sir?
Ma'am, could you send your PPT to the conference mail ID, ma'am?
I have a lot of slides about my application, so I will change the slide by myself, sir.
Good afternoon, ma'am. Hello.
Yes, sir.
Can you audible, ma'am?
Yes, sir.
Ma'am, please share your PPT, ma'am, through conference mail ID. Send it to your yeah.
Screen share has been disabled.
The screen sharing is disabled, so.
Sir, already, ma'am, already I told that. Okay, it's not give the screen sharing option to you. You follow the each and everybody the
Okay,
same
sir.
thing.
Okay, sir.
Okay, please share your send it your PPT through email ID. Dear participants, from afternoon session also, please share your PPT before 2:10. Okay, so then only we can allow the oral presentation allotted for the each and every. Okay, so please share your PPT as soon as possible below 2:10, the afternoon session. Okay, ma'am. I give the chance to afternoon N55. N55, please respond.
Yes, sir.
Okay, I give the chance afternoon, ma'am. Please send it as soon as possible, your PPT. Okay.
Sir, I send it, sir. It's uploading, sir.
Yeah, that is we are waiting. Yeah. The next resource person waiting. So then we will move for next session.
Okay, sir.
Okay.
Let's get, dear participants, let's move for 5 minutes of break, a short break. We expect your presence at 12:30 exactly. The second technical section will take place at 12:30 p.m. Please do present. Thank you.
Just hold on. என்ன சொல்றீங்க என்ன இங்க இருக்கு சொன்னாங்க இருக்கு. This color. The 5 minutes they continue. Sir, good afternoon, sir. Can I tell you, sir?
Hello, sir. Good morning.
Yeah. Sir, are you ready, sir? Let's start session.
It's ready.
Okay. Dr. Wani?
Yeah.
Yeah, okay. Just wait.
Welcome back, everyone. Now we are entering in the second technical section of this NCIST 2021. I now request Dr. P. Wani, Research Associate, Department of Physics, VIT Chennai campus, to introduce the speaker. Welcome, ma'am.
Thank you. Good afternoon, ladies and gentlemen. It's a great pleasure for me to introduce our speaker, Dr. G. Kalaiselvan, from the Cavendish Laboratory, University of Cambridge, United Kingdom. He obtained his PhD in the field of material science and MSc in material science from Bharathidasan University and Anna University, respectively. His current research focuses on condensed matter physics and deals with high pressure and low temperature. He has published 43 research articles in reputed journals since 2011 to till date, and additionally, he has lots of publications in conference proceedings as well. He has also delivered lectures in various conferences and scientific meets. He has received Best Student Proposal of the Year 2018 for Team Symposium on Advances in Functional and Exotic Materials at Trichy. He has received Young Researcher Award in the year 2016 at Bharathidasan University, Trichy. And he was the JRF and SRF Fellow by UGC BSR during 2013 to 15 and 15 to 2016 respectively, and Project Fellow by DST from 2010 to 2012. He's also having membership in Oak Ridge National Indian Society for Technical Education, Material Research Society of India, Indian Physical Association, and IEEE journals. He has visited as many research labs in foreign countries, Oak Ridge National Laboratory in US, and International Conference on High Pressure Science Technology 2015 at University of Complutense, Madrid, Spain. And he went to Institute of Solid State Physics, University of Tokyo, Japan. And he was worked in high pressure physics, Nippon University, Tokyo, Japan, Osaka City University, Osaka, Japan. So here we have our eminent speaker who is going to enlighten our minds about the developments and importance of high pressure studies in high temperature superconductors. Ladies and gentlemen, please join me in welcoming Dr. Kalaiselvan. Welcome, sir. I hand over the session to the speaker, Dr. Kalaiselvan.
Yep. Thank you, ma'am. Thank you, Dr. Wani, for his nice introduction about me in this section. You guys, can I able to see my screen?
Yes, sir.
Yeah,
it's visible.
thank you.
Yeah.
Yeah, nice. Before that, I would like to thank the organizing committee and head of the institute and the convener of this NCIST 2021. Today, this is my pleasure to share my knowledge and research work on my field in the high pressure material like superconductor and some other strongly high temperature and some superconductor as well. The title of presentation is Development and Importance of Pressure Studies in High-TC Superconductors. Yeah, before going to the topic in the superconductivity, we need to know about the resistance. This is the important parameter to restrict the current, and also it restrict the new technology as well to becoming the recent era. The electrical resistance is similar to like a friction. For example, in the water flowing the pipe, a long narrow pipe provide the more resistance to flow than the short fat pipe. This is the same as here when applying the current in the long thin wire to provide the more resistance than to the short thick wires. Resistivity is nothing but the electrical resistance to conduct the conductor to measure how difficult it is to push to charge along with us. Its example is R equal to resistance equal to resistivity divided by L into A. Resistivity is majorly depend upon the length and the cross-sectional area of the material. So conductivity is just inversely proportional to the resistance. Yeah, we all are known that insulator material classified into 4 types, so like insulator, semiconductor, conductor, and then finally superconductors. Insulator is nothing but it does not conduct electrical current. It's not, but come to the semiconductor. Yeah, it will conduct the current in one direction. After certain amount of current is following, the voltage drop is almost constant. In the conductor, it's likely like a simple wire. The current can flow at any direction. There is no fairly low resistance. If in advanced technologies, that means superconductive special material that certain temperature, that means has zero resistance. It has conduct the current without loss of energy or resistance of this material. The same time, it used to lot of application oriented point of view, and some haven't to be realized and in the large scale yet, and some has been done it. So here the figure is clearly shows how the superconductivity and the semiconductor and conducting property will be varied with respect to temperature. And the superconductors see the transition was dropped around some certain temperature. It is called superconducting transition temperature, will be explained in the following slides. Hello. Yep. There is the figure is shows that the periodic table, some of the material shows the superconductivity at ambient condition, and some the green labeled material is shows the superconductivity under higher pressure. When applying pressure, it will be normal material to become the superconductor at a higher pressure, like above 20 or 25 gigapascal. And the yellow labeled sample, like carbon, is called the modified form. For carbon is purely the insulator and will be modified in structure like C16 or graphene. It will become a superconductor. So that's called the periodic table. It's clearly shows what are the material associated to superconductivity at ambient and higher pressure conditions. Superconductivity. Yeah, superconductor is nothing but the ability of material to conduct the electrical current without resistance. That's called superconductivity. It was discovered by H. Kamerling's once in 1911, and he got the Nobel Prize in 2000 and 1913 for his discovery of superconductivity. So for normally the metal become the low temperature, it will be have some residual resistance at 0 temperature. But the superconductor can be transferred transfer from normals to superconducting state. It will drop to 0 resistance. So the temperature is called TC. It's a transition temperature. The physical phenomena of the superconductor and important is superconductor can the large amount of current with a little or no loss of energy. That it's depend upon the Joule heating law. There is no heat is produced when traveled through the current from one end to another. There is no heat is produced. There is because of there is no resistance on the sample material. So this material is called a superconductor, and it's mainly classified and explained by the 2 category. One is the perfect conductivity, like means zero resistivity, and one is perfect diamagnetism, that is a negative magnetic susceptibility. Unfortunately, most of the material must be in extremely low energy state at very low temperature. The recent research is underway to develop the compound to become the superconductive to higher temperature, like a room temperature application. So that currently an excessive amount of energy must be used to cooling the process, making superconductor very insufficient and uneconomical. So that's the reason we need to focus and find the new superconductor at room temperature application. Here we explain some of the basic properties of superconductivity. It is explained by the following theories: Meissner, BCS, Josephson effect, and the Joule-Keating law, isotopic effects. Zero resistivity and negative susceptibility already discussed with this previous slides, like a Meissner effect. And the critical magnetic field is nothing but some minimum amount of magnetic field will destroy the superconductivity, nothing but to kill the superconductivity at a certain level. The critical field is called the field is called the critical magnetic field. And Cooper-Fair coherence length and the London penetration depth also explained by the following slides as well. Here we explained the Meissner effect. Meissner effect, yeah, this is the one. This was discovered in 1933 by Meissner and Assenfeld. It's means it was clearly shown in this figure, left side figure. When the material was placed into the magnetic field, if in the normal state, above the superconducting temperature, the magnetic field is absorbed from the material, and it would be transferred from interior of the material and comes out. But when material becomes the superconductor, the magnetic flux is pushed out, and it magnetic field away from this material. That's materials purely act as the diamagnetic. That's why we called as a very superconductor is. All the diamagnetic materials, not the superconductor, but all the superconductor behave the diamagnetic property in certain temperature. That's called the superconductivity. Here the images shows how the levitation is appeared when the material becomes the superconductivity, and the bottom figure is clearly shows how the Meissner effect is affecting the conventional and unconventional superconductor. The green lines is fully followed the Meissner effect. It is the unconventional superconductor because the magnetic field is pushed out from this superconducting material, and this is the purple images is clearly shows that how the magnetic field is penetrate into the superconducting material in the vortex state. That means the type 2 superconducting. And the yellow region is clearly shows that this is called the normal state, normal material state. That means either ferromagnetic, paramagnetic, and whatever the material at its properties. And then PZS theory. This is the one of theory found in 1957, and he got the Nobel Prize in 1972 for his one of the predominant theory was discovered by Bardeen Cooper Serifer, and this is the main mechanism to playing the major role in the superconductivity, how it would be reacted. Here, the electron lattice electron interaction is stronger than the electron interaction because when that means that for normal conductor, if the electron is majorly to carry the current from one place to another, but here the electron normally the electron will be repelled each and every each and each. But in the superconductor, the electron is formed as the Cooper pair due to the lattice vibration of the superconducting material at the certain temperature. That means below the superconducting temperature. This pair is called a Cooper pair, and this length of this combined electron length is called coherent length. It will be traveled from certain distance from into these lattice of the superconducting materials. Further, we can explain some of this how the superconducting material can be classified depend upon this temperature. So it was classified in two types. One is type 1 and another one is type 2 superconductor. Type 1 superconductor is nothing but the conventional superconductor. It was very low temperature, and it's follow the Meissner effect. and there is no mixed state was present in this type 1 superconductor, and also it called as the soft mass superconductor like lead, tin, and mercury. These are the single element always called as a type 1 superconductor. Not all the single element, but some of the materials called the type 1 superconductor. And the type 2 superconductor is the high temperature, it called as a high temperature or unconventional superconductor, because there is gradual loss of magnetization. There is no sudden drop. Here we can see that there is two critical field is there. One is HC1 and another is HC2. It's depend upon the gradual loss of magnetization. And the main trouble is here it does not exhibit the complete Mason error effect. And there is the mixed state also present, and this is why it's called the hard superconducting material. All the high temperature superconductor is behave in the property of type in the combined with type 2 superconductors. Majorly, the superconductor can be classified depends upon the four types, depend upon the magnetic field, how it will be reacted, and a theory like how the BCS theory obey with the superconductor, and depends upon the critical temperature, and followed by the material, the superconductor can be classified. Initially, the single element can all exhibit the superconductivity, and some of the binary elements, some alloys and composition of this single element can be explained the superconductivity. And as follows, in 1986, the cuprate superconductor is formed as a high temperature superconductor. It became above the boiling point of liquid nitrogen. Here it was the main, 1986, there was the important in this field of superconductivity. As follows, several superconductor were also founded up to last 110 years. And in 2018, iron is become a superconductor. It was the major impact in this field of superconductivity. Also, the recently in 2015 onwards, some hydrate sulfide materials become the superconductors. Behave into the room temperature. It's not into the in this application point of view, but some other collaborating researcher and some of the worldwide researcher is focused on this H2S sulfur hydride superconducting materials. Here I would like to show some of the slides to explain how with the superconductivity become the important in this daily life. Up to 1986, there are superconductor found at a very low temperature, below 30 Kelvin. And in 1986, Bernards and Muller discovered the superconductivity in barium lanthanum copper oxide at 30 Kelvin. And then instead of changing this lanthanum, changing the yttrium instead of lanthanum, the superconductivity hike up to 90 Kelvin. Further, the doping into this yttrium side, they are changing, instead of yttrium, they are changing the mercury and cerium and calcium. The superconductivity has increased up to 133 Kelvin. It was found at above the 77 Kelvin, like the hydrogen boiling point of liquid nitrogen boiling point. So why it is important for the nitrogen boiling? Because it was we can prepare the nitrogen, liquid nitrogen very less cost, and it was economically friendly. So then the superconductor will become the come to the application point of view after discovering of these two guys like Berners and Muller discovered this cuprate based superconductors. As follows, some other magnetic property combined with the magnetism and the superconductivity to become the superconductor like MgB2 and iron-based chalcogenides, nictide and chalcogenides superconductors. Here we focused, my research mainly focused on the iron-based nictide and chalcogenide superconductor because of its structure. Here it was aligned in the, it was discovered by Kamikera once in 2008. Here we can see it was arranged in the layer type, the insulating and conducting layer is arranged in the sandwich type, and it was transferred from electron to conducting electron from conducting layer to insulating layer. That was helping to increasing the charge carriers and become the superconductor at below certain temperature. Instead of changing this rare earth of lanthanum, we can find the superconductivity at 50 Kelvin, used samarium as the replacement of La instead of La. As follows, there are 4 types of superconducting families in the iron-based material. One is 411, no, 4131 and 122 and 11 types of material. We choose this FeSe, I mean this image D. I choose this material because of its simple structure. It was arranged in a tetragonal structure, FeS for tetrahedron sides. It is a simple structure. It will be carried and replace the sum of the element in the either Fe or Se sides. So my motivation is how pressure is play the major role in this field of superconductivity as well as the strongly correlated system, because we can find the superconductivity at ambient condition, and then the superconductor become too higher when applying the external pressure of this material, because we already shown that the mercury based material shows the superconductivity at 130 Kelvin when it is applying higher pressure up to 30 GPa. Here we can see the images. It's shifted up to 164 Kelvin at 30 GPa. So that's why that's the important to we need to we can focus on this find the superconductor under pressure. It's more helpful to the people to investigate and synthesize the new sample for the following periods. Up to now, the highest superconductor was observed in 270 Kelvin and in last year 2019. It was applying pressure up to 100 GPa. That means the higher pressure, but it's not in the application point. It's not come to the application, but we can find the superconductivity and the phenomenologically it was good. So further still they are studying to optimize the stability to come to the room temperature applications. The main application of this, if it is come to the find the superconductivity at room temperature, it will be very helpful to enhance the technological in this the technological world. Up to now, there are several superconductor was used in this medical application, like we are measuring the MRI scanning and nuclear magnetic resonance. We used niobium titanium for MRI scanning and nuclear magnetic resonance spectroscopy. We are using niobium tin superconductor for its applications. Further, in the power application point of view, there are we are used copper wire to transfer the current from one place to another. That means transfer from to home and whatever it is. There is some energy losses is appeared due to the heat was produced and due to this some restriction of restriction due to the resistance appear in this material. So instead of copper wires, if you find used in the superconducting cable, that means they can carry the current without loss of energy. That means there is it will be a lower losses, and we can get the higher efficiency. It's also the environmental friendly. Same times is the higher current can be passes through one place to another without loss of energy. Most of the application of superconductive may be depend upon this the following factor with respect to magnetic field and critical current density. It was mostly used depend upon the how the critical current, I mean current can carry the material from one place to another. I mean carry the current and how destroy the material with respect to current. So it will be depend upon this. We can use this application like cable, I mean coaxial cable, generators, motor, fusion magnet, and MRI spectrometer, MRI magnet, and somehow in the magnetic levitation. We are recent, I mean, last few years it was worked in Japan, China. They are used the fastest train. It was used by magnetic field application. It was called as the levitation train. And yeah. Here, I would like to explain how the superconductivity, I mean, pressure waves play the major role in superconductivity. because it was tuning the superconductivity can be tuning the reasonable factors such as internal pressure like chemical doping, and external pressure. We can give the force externally under to the sample, and with respect to temperature and high magnetic field. Majorly, the magnetic high pressure is reduce the atomic distance between the two atoms and will be enhance the charge carriers from one atom to another. So it enhances the superconductivity at lower state to higher state. Here the images is clearly shows how the superconductivity be varied with respect to pressure under changing the anionic height of the Fe layer of these superconducting materials. Here FeAC shows the highest TC at 37 Kelvin when applying pressure up to 4 GPa. That's why we are choosing this sample to changing the physical sum of the transition metal doped into the Fe sites. How the TC will be varied with respect to chemically, I mean internally and externally doped, externally applying pressure on this material. I already told because it is a simple structure of FeSE, so I can choosing this sample, and how essential to understand this material when applying pressure of FeSE. It is given the clear mechanism and some of the origin of superconductivity and unconventional superconductor, and also we can discuss the electronic properties of novel superconductor with respect to ambient and external pressure condition, and easily correlate with respect to structural and superconducting properties in the ambient and higher pressure. At the same time, it understands the similarities and the difference between the high temperature superconductor and other future known superconductor like ambient and higher pressures. So during my PhD period, I go and prepare the sample in various institutions in Professor A.K. Ganguly, IIT Delhi, Department of Chemistry, IIT Delhi. He was the director in ISAT Mohali, and we get the sample from NPL Delhi, from BPS Avanat's group, and Prapat Mendel from Sakha Institute of Nuclear Physics, Calcutta. After collecting the sample, basic studies was analyzed. We go into the high pressure studies. We used both labs. Professor Arumugam lab. This is one of the center. We used high pressure transport resistivity measurement, because mostly in India, all the peoples are working high pressure. I mean, several peoples are working in the field of high pressure. They are studied in structural studies because this is the easy way to studies, because we can put the sample instead of I put the sample inside of this intermediate between the two diamond. It will create the pressure, and we can measure the transition, I mean structural studies of this material. But in Professor Armugam's group, they are working in transport measurements, transport and magnetic measurement of this sample, because the very difficulty is to making the contact. I mean, we made the 4 contact on the sample with minimal size, and they are working very good, established very good laboratory in the field of high pressure research center in the unique center in India. And also we learned some of the experimental techniques and advanced techniques in UK Voras group, University of Alabama, Birmingham in USA. Now the advanced technology, at the same time, the advanced technology I was used in Cavendish Laboratory, University of Cambridge, UK. So still it's on the progress of this, developing new high pressure cell, how it was going to for future generations. Why the pressure is important for what are the material, like what are the nanomaterial, whatever material, strongly correlated materials, how it is important means it was changing the parameters like bond length, bond angle, and lattice constant. It will be varied without modification of there is no structural changes appeared when during this. The structural changes is appeared when during the compression of this material, but we don't want to change any chemical changes on this material, so we can easily change the structure and the density of state in the Fermi surface as well. The same time, to control the volume changes by shortening the atomic distance that we called already shown in the previous images. It's shortening the atomic distance of this material and modifying the crystalline structure. Same time, the hybridization will be appeared when compressing this material to change the valence changes, and bond gap and bond width as well. Basically, the pressure will be classified into 2 types. One is hydrostatic and another one is uniaxial. Hydrostatic is nothing but followed by the Pascal law. It was the material placed into the liquid medium. When compressed into liquid, the pressure was transferred from the liquid to the sample to all the directions. But uniaxial is nothing but the Paschen effect. When the material is compressed from the one side, it will be generated. It was compressed and elongation the side view, and it will be compressed at one layer of one side of the either x-axis and x and y-axis of the sample, but not in the z. I mean z and the x-axis, not in the z and y-axis, not in the x-axis. So here we used for both the pressure studies to how it will be varied with respect to uniaxial and hydrostatic pressure of this material. Most of us superconductor can strongly affect with respect to pressure. Still now it will be highest superconductor is found at 270 Kelvin and 200 GPa in lanthanum tetrahydride superconductor. Recently found in 2019, but that's why we are still focusing on high pressure research to how not only the superconductor it will be varying the property instead of Fermi surface, and how the vortex spinning will be varied with respect to pressure. So that's the main ultimate aim to improve the superconductivity with respect to pressure instead of chemical doping. So yeah. This is some of the equipment I was used. Mostly they are used for studying high pressure condition. This is 9 Tesla ppms VSM to measure the low temperature around 300 to 2 Kelvin with respect to pressure, with respect to magnetic field, low temperature and a higher pressure. And this is the figure. Images is shown to measure the magnetic properties under pressure up to 150 kilobar, like 1.5 GPa. And this is the CCR, closed cycle refrigerator variable temperature insert system to measure the resistivity with respect to pressure, not in the magnetic field. It goes up to, these are the pressure cell. We are used piston cylinder pressure cell, and this is modified Bridgman annual pressure cell. And this is the cubic annual, and how to mount the sample inside the sample. The difficulties here, the sample size is 1 mm. Did you think about this? The 1 mm sample we need to mount, make the 4 contact, and then we measured. We found we transferred the current from the 2 leads, I plus and I minus. We observed get the voltage difference between the 2 leads, inner voltage leads. This is how we measure the. Yeah, we can put the sample in the capsule. How we can measure the pressure on this exact pressure on this sample, because here we used the tin as the pressure manometer. Tin is the superconductivity at 3.72 Kelvin. When applying pressure, the tin was the superconducting transition was shifted towards low temperature. So this is the important images. A calibration was usually used to monitoring the pressure when the sample is inside the pressure cell. Yeah, when during the magnetic measurements, we used fluorinate 70777 oil with ratio of 1:1 to maintain the hydrostatic pressure medium up to 1 GPa, 1.5 GPa to generate the pressure inside the pressure cell. So here I have to show some of the images. Here, this is what we mount the sample. This is 1 mm sample. We place it into the obturator. This is the piston cylinder pressure cell. It was built in beryllium copper, and inside it was the inner cell was created in nickel chromium aluminum alloy to build the higher pressure up to 3 GPa. So pressure will be varied with respect to pressure and what type of pressure cell we are used, because there is every materials and every system has a particular limitation to generate the pressure, right? So this piston cylinder pressure cell is usually used up to 5 to 3.5 GPa to generate the pressure, measure the resistivity measurements. Here we use this definitely 7373, either definitely 7474 oil to use the pressure medium. Pressure medium is mostly preferred depend upon the solidification point. That means the solidification point is nothing but how the material when the material is solidified the certain temperature at the certain pressure. Like the solidification point of 7474 is 3.4 and solidification point is 7.7373 is 2.9. Mostly we 7474 used as the pressure to medium to enhancing the higher pressure to maintain the hydrostatic pressure up to certain levels. Yes, consider about the sample size is 1 micrometer and the width of the sample is 0.6 and the thickness is 0.2 mm. Here the bismuth is the pressure manometer. We can simultaneously mount bismuth and sample in the same material, and instead of changing the parameter, we can found how the TC will be, how the TC not the TC, how the transition will be disappeared with respect to structural transition appeared with the bismuth. We can found the pressure in the inside of the capsule. This is another pressure cell we are used to mounting the sample. This is the modified Bridgman animal cell. Basically, they are used cubic animal press in Japan. This is the large equipment. It goes up to 8 to 10 GPa. Instead of this one, this is the simple and compact one. We can usually use it in cryostat measurement, cryostat system. But yeah, because the main difficulty is the size of the sample. This is very hard to making the contact using the here the silver paint used as the conductor to connecting with the gold wire. 10 micrometer gold wire is connected with the silver paint to the sample and will be clamped with this gold foil to given the current to the two leads I plus and I minus and get the voltage difference between the two voltage leads. These are the results I get it in University of Cambridge. This is yttrium barium copper oxide sample. This is, can you imagine that this is the sample size is 0. Yeah, this is just like 150 micrometer. This is near to the human hair thickness of the human hair, and we can make the four contact on the sample, and we can measure the resistivity with respect to pressure, and we can measure the transition temperature with respect to magnetic field, how it will be shifted, and we can calculate the RHS for how the penetration and how the Fermi surface will be acted with respect to pressure as well in the YbCO2 sample. These are recent studies we are going on under progress in our laboratory. And this is the next advanced technology we are using in the University of Alabama, Birmingham. Instead of wiring of the sample, we used a tungsten carbide. Tungsten used as the leads. They are deposited in the diamonds, top of the diamonds, and it was covered and encapsulated with the diamond. Diamond was deposited in the top of the diamond surface, and the edge was opened due to the micrometer edge was opened. The tiny piece was opened. Because of it, we need to get the contact on this sample. This usually made at the pressure contact when place the sample in this intermediate between two samples. Intermediate between the diamond, we can applying pressure. It will be generate. It will be make the contact on the leads. It will be generate the pressures. Yeah. Here the clear images I have shown it here. This is the tungsten electrical reeds, and when we making the gasket and make the hole, and this is the sample. It's around 80 micrometer. This is more smaller than the thickness of human hair. So here we used steatite, like nothing but the Al2O3 powder used the pressure transmitting medium. That's a solid pressure meeting medium. This is not the purely hydrostatic. This is a quasi-hydrostatic. Here the steatite used as the pressure transmitting medium. At the same time, it acts as the insulating of the gasket, because gasket is the stainless steel. It was the purely metallic. When they place the sample in intermediate, inside the hole, it will be touch with when applying pressure. It will easily touch with this gasket. So it will create the sample contact with the pressure cell. The contact resistance will be appeared. So avoiding this, we can avoid this unwanted purpose. We put this steatite as surrounding the sample. It produces the insulation of this gasket, and at the same time it acts as the pressure transmitting medium, quasi-hydrostatic transmitting medium of this pressure cell. And this is the pressure cell I was worked, and it was generate. This is the lab view program we installed it, and we playing the gas pressure on it. We generate compression of the sample and measure the resistivity with respect to temperature up to 12 Kelvin. And I would like to show some of the results I was done in the University of Cambridge and Center for High Pressure Research. I get this element from Dr. VPS Avana's group, NPL, National Physical Laboratory, New Delhi, the FESE sample. We can these are the well-known sample single crystal FeSETE. It shows superconductivity at 2 Kelvin, at enhance the superconductivity at above 20 Kelvin when applying pressure. So I'm thinking that we are doping the Ni instead into the Fe sides, how the TC will be varied. It was shifted towards low temperature, and a higher doping, the superconductivity was completely vanished. So I have used 0.01% doping in this sample, the red one, for our high pressure studies. And the basic properties and structural and homogeneity and basic properties are investigated by Avana's group and published in Journal of Superconductivity Novel Magnetism 2016. Further, I'm going to measure the high pressure resistivity measurement of this sample. So investigation, this is high pressure resistivity structural studies I was measured in Advanced Photon Source National Physical Laboratory in Chicago, USA. So we just putting applying pressure, how the structure will be changes, then how the structure is mostly important to changing the TC with respect to pressure and towards the low temperature. In the structural studies, at ambient condition like 0 GPa, it shows the pure B4 NMM tetragonal structure. The major peaks are clearly present, shown his structure of this material, and the purple 111 and 20 is make us the here copper is the pressure marker. We can changing the pressure with the you can calculate the pressure from the pressure marker. When increasing the pressure, the structure was changes. It's depend upon the some the shoulder peaks are appeared in this. Shoulder peaks appeared to start in the major peaks is here O2, and some of the peaks are appeared in 220. Here we can see some of the external peaks are present here. So that means it was present the new phases into the B4 NMM structure. And up to 7 GPa, the P4 NMM tetragonal phases appeared. Above 7.5 to 15 GPa, the mixed phases of hexagonal NIA phases and tetragonal phases appeared. Above 15 GPa, it was completely transferred from NI hexagonal phases, P63 MMC hexagonal phases appeared. Once this pressure is released from 52 GPa to 0 GPa, its material comes to this original position. This is more important because the come to original position is more stable, and because this type of material can be used for this application point of view. So this is the image was calculated from the GSAS2 software, and structure was clearly analyzed and clearly analyzed, and how structure will be changes with respect to pressure. And here we can clearly see how the structure will be changes from one phase to another phase, P4 NMM to hexagonal phase. The volume is be decreased from 0 to 7.5 GPa, and here we can some small hump is there, and will be the combination between combined with the B4 and P63 phases appeared in 7.5 to 16 GPa. The sudden drop is appeared up to 15 GPa. Then it started to applying presence of Na hexagonal phases. It was clear. It was calculated by the Bridgman-Morgan equation. Here it shows. These are the correlated studies I was measured in magnetization measurement. The TC was shifted from 8.6 Kelvin to 14.7 Kelvin up to 1 GPa with a rate of positive pressure coefficient of 6.06 Kelvin per GPa. At the same time, we measure the magnetic field with respect to pressure. We can found the diamagnetic hysteresis, not the clear diamagnetic hysteresis. Usually, the superconducting material, below the transition temperature, it clearly shows the pure diamagnetic hysteresis. But instead of here, we put Fe and Na is plays the major role due to this Fe magnetic moment. There is some positive magnetic moment are present here, so it shows the ferromagnetic curve on this material. Here we calculated the upper critical field. We measure the. This is clearly shown. This material it was the type 2 superconductor because there is the two critical fields there. One is Hc1. We calculated from the straight line. We can put the straight line on this material. The inset of figure clearly shows Hc1, and Hc2 is here when it is joined into the 0. This is Hc2. So compare then the other material, the HCO is a little higher than the FeSe parent FeSe material. When changing to this, increasing the temperature, the magnetic moment of this magnetic moment will be increased with respect to applied magnetic field. It's due to the positive Fe magnetic moment of this FeNA SETE samples. At the same time, we measured the high pressure resistivity towards low temperature under pressure up to 20 GPa, up to 3 GPa. We calculated the resistivity measurement using piston cylinder pressure cell. Above 3 GPa, we can go for a discerner diamond anvil cell. We measured the resistivity. And, the TC has shifted from 9 to 30.5 Kelvin at 3 GPa with a positive rate of 7.19 Kelvin per GPa. Further enhancing pressure, the TC has shifted towards low temperature. It's the same time the normal state resistivity also decreased with respect to pressure. It is mainly due to the increase of charge carriers in the density of state. Generally, the reduction of pressure can be play the major role to reduction of electron phonon scattering to enhance the density of state on the Fermi surface to become the metallic. Here we can show the semiconducting nature will become the metallic when it is it's due to the structural changes from Fe tetragonal to Na hexagonal phases. Above 7 GPa, 7.5 GPa, the TC will be decreased from 19 Kelvin and will be disappeared at 10.9 Kelvin. Here the images clearly explain it. And this is the general phase diagram was developed with respect to pressure. And this is when increasing pressure, the TC has, the purple will shows the TC has increased dome-shaped curve at maximum pressure of 30 GPa, maximum temperature of 30 Kelvin. And it will be decreasing. It was increasing pressure. TC was suppressed, and because of and up to 14 GPa, it will be decreased due to the limitation of the temperature in cryostat. It goes up to 12 Kelvin, so we can't measure the TC below this pressure. And this is the mixed phase of tetragonal and hexagonal phases. So TC was decreases. When after completing it completely changing the NAA's hexagonal phases, the TC was completely vanishes. And here we can calculate the density of state calculation, theoretical calculation. The structure was changes at the Na tetragonal and how it will change it to Na hexagonal phases. Further studies, it will be helpful to, it's really give some additional information about how the electronic structure possibly charge transfer under pressure related to the corresponding changes of TC. At the same time, the negative pressure coefficient above GPa may be due to the magnetic instability and structural changes at a higher pressure. This is the major phenomena will appear when TC was due to the due of its TC changes. Our high pressure results of above 3 GPa indicates the decrease of pressure coefficient that mainly due to the reduction of Fermi level, reduction of charge carriers in the Fermi level at lower TC. Further, some additional studies we are required to. At the same time, the ionic distance also not the important parameter. It's one of the important parameters. Not only the important parameter. Sometimes it's additional studies like neutron diffraction studies will give the clear information about the how give clear information about how the magnetic fluctuation of appeared during this under pressure of this material. So definitely, it will be give some structural and magnetic transport properties. Give very helpful to understanding the understanding and finding the new high temperature superconductor. How it will be varied. What are the material will be doping inside of simple structure of a FESE material. So this is some of the point I'll be find out in these recent studies. Yeah, thank you.
Thank you, Dr. Kalaiselvan. Dear audience, session is open for discussion. If you have any doubts, kindly unmute yourself and ask your questions, or if not, just post your questions. I will convey the question to the speaker.
Yeah, I think superconductor is the common in all the field, but high pressure is there are unique people also working on this field, but superconductor is common. So you guys can ask the question on that.
Question from the audience. Sir, can you give the open source software reference to draw the magnetic structure with domain wall orientation?
Did you ask about the software?
Yeah. To draw the magnetic structure.
Usually they are used. We need to find the neutron diffraction first, and then we can use how the fluctuation will be changed with respect to pressure. Actually, yeah, I will send this to your to his mail. What are the software is available in to draw the magnetic structure of this material? Really, I forgot on this the software.
Okay, fine, sir. Dear participant, once we get it, we will share through mail. Yeah. One more question.
I will send the mail. Yes, ma'am. Yeah, you can continue.
One more question, sir. Can possible to change the chemistry of materials by pressure?
Chemistry of material, it's most of it's not possible because the physically it was changed. It was changed. Some hybridization is appeared on this material, right? Because it was changed from one phase to another phase. Definitely, chemistry will be appeared on this during higher pressure. Because recently founded H2S as the superconductor, it will be changed into H2S to H3S. So definitely some chemical bonding is appeared on this during the pressure conditions. Yes, it was.
One more question from the audience. Your all materials are not having transparency in visible region. Then how it can be potential materials, electronic and energy conversion applications?
Sorry, once again.
Yeah, your material, all the material is not transparent in visible region. Then how could you adapt, or how could you say it as a potential material for electronic purpose and energy conversion applications?
Because you guys are thinking just on the, it's not the absorption view, not only the, you don't want to point out the optical point of view, you just think about the electronical point of view. We just carry the current instead of using the basic properties of like optical absorption. We can use these electrical studies of this material. So we can see the clear transition of this material. Definitely it will use the potential application of higher temperature. So it's not only depend upon the single property analysis, and we can check with other properties as well. So it was used in application point of view as well.
Okay, sir. And one more question. Small labs, we cannot afford the facility to grow or the superconductor materials. Big labs like ISC and IIT, they are working in superconductor materials. So how can we afford that facility in small labs? Can you give some ideas or for
Yes, ma'am.
researchers?
Usually the small labs, there is due to the funding facilities, because basically this, when we are preparing the superconducting material, we use prepare the sample inside the cloud boxes. So it will be a highly high economical. So due to the funding, lack of funding, there most of the cloud boxes in present in this some higher institution. Yeah, that's fine. You guys just approach this. We can search all over all over, just on the India. You can search in some of the major laboratories, and you just send an email and approach them. What are the material? How the purpose you have used? What are the materials going to prepare? You just write an email and a small proposal. You just given to him. If they are accepted, they definitely they'd call you and prepare. You can go and use these facilities, because I don't have facilities in preparing the sample in our laboratory during my PhD period. We're just writing the proposal to NPL, Avana's group and some other Professor A.K. Ganguly sir's group, and they allow me to come and to work on in his laboratory. So direct approach is the main important thing. You can just approaches, and given before that we need to clear idea of what the sample you are going to prepare and what are the importance to study on this material.
Okay, sir. Questions from my side. I'm not familiar with superconductors.
Yes,
but as you mentioned, superconductivity can be achieved by tuning or by doping the chemical materials, right? In one slide, yeah, you have mentioned that we can tune the superconductors of chemical doping with external pressure as well as temperature.
Yes.
So what is the limitation for chemical doping? What are the limitations for chemical doping? And is there any criteria or key points
Yes, ma'am.
to choose the chemicals, or as well as the percentage, addition of a percentage of chemicals?
I got the questions.
Yeah.
Actually, when the doping of the material, it's called as three types. One is underdoped, optimal doped, and overdoped.
Okay.
So there is a certain limit as there. If it is below underdoped sample means it will be clearly it shows the superconductivity, and also I'm talking about related with the superconductor. I'm not the general. Just on the focused on superconducting point of view. If it is doping, like if we, I can share this, show some of the slides here. Can you see the slides?
Yeah.
This is when we are doping in doped Ni in Fe sites. This is underdoped sample. That means if underdoped samples, below 0.01, like 0.001, 0.001, it was the underdoped sample. That means then TC has enhanced. Once it's optimal doped means 0.01 to up to certain level, when the superconductivity was destroyed up to the certain level, this was underdoped optimal doped. That means when applying pressure, TC has enhanced or decreased. And that means the overdoped sample means definitely the TC will be suppressed with application of pressure. There is certain limits usually if you are used here, you can choose the Fe1, Se, pair material is Fe and SETE, right?
Yeah.
So here X is equal to the variable. So you can change the variable from depend upon the material and how the electronic states are. We can choose the dopant material, and at the same time the concentration is important, and the changing the limit of this material.
Yeah, in case of adding rare earth elements, digestion of rare earth elements in metal compounds is it's a difficult one. More concentration of rare earth we couldn't digest in metal compounds easily.
Yes, ma'am.
Yeah, so in that case, in rare earth cases, how could we incorporate the rare earth in the metal components?
Yeah, that's a good question. And the same
And
time,
is would be depends on the material we choose, the metal we choose, or rare earth. It depends on rare earth or depends on the metal.
yeah, it's depend upon the metal we need to choose, because for FESE material we choose. Just a minute. Yeah. Here you can see the transition metal is also there, like FeSe, and lanthanum is also there. This is the rare earth element.
Yes, yes.
So depends upon the direct we can't deposit it on this rare earth lanthanides into the transition metal. So instead of it, we can choose some other material related to the rare earth element. We can, here we see the lanthanum and O is the insulating layer. So Fe is the conducting layer. So we can't show directly we can't dope the La on the Fe sides. We can dope in the O and La sides. We can dope F and the O sides. I mean La 1 minus X and Fx. So this is the way need to change the transition. Changing the rare earth element into the rare earth transition metals.
What is the percentage of doping? What is the limitation for percentage of doping of rare earth elements?
Limitation. No, ma'am, I don't have any clear idea on that. So it's depend upon how the concentration will be varied. We just focused on how the particular choosing some. I mean, 0.1, 0.2, 0.3%. The step is increasing, and after taking the measurement of the sample, we can clarify into these are the optimal dopant level, and these are the optimal. We can classify on that. So
okay, thank you, sir. And one more small question.
Yes.
As you said, making context is a big task in preparing material for superconductors. So what will be the sample thickness for making good contacts?
Sample thickness.
Sample thickness, yeah.
Yeah, it's depends, ma'am. Maybe it's our requirement is minimum size is more preferable. It's 0.5 mm is most probably we are used.
Okay. Thank you so much, sir. Audience, anybody having question, you can post or you can ask directly.
I will send the software details to our conference mail, and you can share it to him.
Yeah, thank you, sir. And I hope the audience have no questions. So I would like to take this opportunity to express my heartfelt thanks to Dr. Kalaiselvan for spent his valuable time with us. And we believe that the knowledge you have shared about development and importance of high pressure studies in high-T superconductors. And once again, thank you so much, sir.
Thank you, ma'am. Thank you for the convener and participants as well. Thank you.
Thank you.
Thank you, ma'am.
It is a real pleasure listening to you, sir. And on behalf of the organizing committee, I extend my special thanks to Dr. P. Vani for being the chairperson. Thank you, ma'am. Thank you, sir.
Thank you. Thank you.
Thank you.
We are now going to take up exercise that crosses between a lung and a crunch. All are requested to be back at 2:10 p.m. There is a kind note to the participants. There is a slight change in the afternoon schedule. There will not be a parallel section at afternoon. I repeat, there will not be a parallel section at afternoon. So join through the same link. The slot numbers for the oral presentation are CG01, CG03, CG05, CG06, CG08, CG09, and CG12, followed by NT12, NT14, NT17, NT19, NT20, NT21, and NT23. I request all the participants, those who are going to do oral presentation, do send your PPT to the organizing committee before 2 p.m. so that we can present your PPT at the right time. Please do it before 2 p.m. I also request NT55 to be ready for the first presentation after the lunch break. Yeah, another note to all the participants that the third technical section will took place at 3:30 p.m. The resource person is Dr. Subhadeep Chakrabarti. He is going to take the third technical section. Thank you, everyone. Have a good refreshment.
time table execution.
நான் கேக்குதுங்களா?
கேக்குது சார்.
ஓகே. ஸோ இதே லிங்க்ல தான் நம்ம 2:15 கண்டினியூ பண்ண போறோம் அடுத்த செஷன்.
ஸ்டூடெண்ட்ஸ் இப்போ நமக்கு லிஸ்ட் கொடுத்துருக்கீங்க இல்லையா, ஒரு 5 ஸ்டூடெண்ட்ஸ் லிஸ்ட்
இப்போ ஆமாம், இப்போ நான் சரி இதில் ஸ்டூடெண்ட்ஸ் கொஞ்சம் பேர் இருக்காங்க. நான் அப்பார்ட் ஃப்ரம் நான் ஃபோனில் பேசிக்கலாமா?
சரி,
பார்ட்டிசிபென்ட்ஸ் இருக்காங்க, நான் ஃபோன் கால் பண்ணுறேன்.
சரி.
அது ஓப்பன் பண்ணுறா தென்ன ஓப்பன் பண்ணி அனுப்புது மேலே அந்த
அதெல்லாம் கை கழுவுண்டா, அதே விட
நீ அதில் போட்டு. ஹலோ, அண்ணா கேட்குதுங்களா? அதான் அதில் இப்போ கொஞ்சம் பார்ட்டிசிபென்ட்ஸ் அப்படியே உள்ளே இருக்காங்க. சரி, அதனால தான் சரி இல்லையா? இல்லை, நான் இப்போ ஆக்சுவலாக வந்து நம்பர்ஸ் வந்து பார்த்தீங்கன்னா கம்மியாக தான் இங்கே ரிஜிஸ்டர் ப்ரெசென்ட் பண்ண வந்தாங்க லாஸ்ட் செஷன். இப்போ கூட வந்து பார்த்தீங்கன்னா ஒரு 3 பேர் தான். இப்போ ஆக்சுவலாக வந்து இதில் வந்து ஜூமில் வந்து என்ன பிரச்சனைன்னா, அவங்க பிபிடி ஷேர் பண்ணணும்னா நான் வந்து அவங்கள வந்து கோஹோஸ்டாக மாற்றிருக்கணும். அப்போ தான் வந்து அவங்க அக்சஸ் பண்ண முடியுங்க. ஸோ அப்படி ஏதாவது கொடுத்தோம்னா இவங்க வேறு ஏதாவது உள்ள லிங்க் மாற்றிட்டாங்க அப்படின்னா இது ஆக்சுவலாக இன்னொரு தாவலையும் இதே லிங்க்கை யூஸ் பண்ணி ஒர்க் பண்ணிட்டு இருக்காங்க. ஸோ அதனால் அது எதாவது கன்ஃபியூஸ் வந்துருச்சுன்னா பிரச்சனை வரும். அதனால் வந்து சரி நம்மளே கண்ட்ரோல் மேனேஜ் பண்ணிக்கலான்றதுனால தான் தெரிஞ்ச ஆட்களுக்கு மட்டும்தான் கோஹோஸ்டாக ஆக்ட் பண்ணுறோம். யார் சேர் பர்சன் யார் கைட் பண்ணுறாங்களோ அவங்க. ஸோ 2:15 ஸ்டார்ட் ஆகுதுன்னா இங்கே இப்போ வந்து பார்த்தீங்கன்னா இல்லை, இப்போ நீங்களே டைரெக்டாக டேக்கப் பண்ணிக்கிறீங்களா, இல்லை நான் இங்கே ப்ரெசென்ட் பண்ணட்டும் நீங்கள் அதுக்கப்புறம் நீங்கள் அங்கே பண்ணுறீங்களா, எப்படி பண்ணுறீங்க? ஓகே, நான் வாட்ஸ்அப் கால் நான் கால் பண்ணுறேன். நான் இதை சொல்கிறது இருந்தால் இல்லை, இதில் வந்து பார்த்தீங்கன்னா ஆக்சுவலாக நீங்கள் திருப்பி ரீகனெக்ட் ஆகிடும், ஆட்டோமேட்டிக்காக இதை ரீகனெக்ட் ஆகும். ஒன்றும் இதில் இஷ்யூ பேப்பர்ல எழுதிக்கிட்டு
CG6, CG9, 2017, 21, 33, 35. Start from the section. So you can start from the number presentation section.
இது அப்படியே இன்ட்ரடியூஸ் பண்ணிட்டு ஸ்டார்ட் பண்ணுவோம். திரும்பி இன்ட்ரடியூஸ் பண்ணி ஸ்டார்ட் பண்ணுவோம்.
Welcome back, friends. I hope you have good refreshment. The oral presentation is going to followed by till now we have received only 6 PPTs. The slot numbers are CG06, CG09, NT17, NT21, NT23 and NT55. I request other slot numbers to send your PPT as soon as possible. The judges for the oral presentation are Dr. R. Karthik, Advanced Scientist, Momentum Performance Materials, Bangalore, and Dr. M. Manivandan, Head of the Department of Physics, Pachamuthu College of Women, Dharmapuri, and Dr. J. Tirupati, Assistant Professor, Karpagam University, Coimbatore. Now the section is over to the judges.
I request NT21 to present your work. Am I audible?
Yes, sir. Absolutely.
Yeah.
Sir, I have to share my PPT or will be shared by
Kindly send it to the conference mail ID, ma'am.
I have already sent on the mail, sir. On the present mail as shared in the group, I have already sent.
Your presentation ID, ma'am?
It's NT21.
Okay, yes, a few minutes, ma'am. A small information to the audience. The next presentation will be by NT55. So be ready. Ma'am, it's time for yours. You can present.
Okay. Sir, 1 minute. I want to say that I am not able to start my video. It is being apologized by the authority or?
Just a second, ma'am. Video will never. Ma'am?
Yes, sir.
Have you received the command to enable your video?
Yes, sir. But when I start, then it is saying your camera is not launched properly. Please check browser media permission settings.
Okay, it's not a problem, ma'am. You can start the presentation, ma'am.
Okay.
Yeah.
Okay. A very good afternoon. Good afternoon to all of you. Myself Priyanka, and I am a PhD scholar from the Department of Bio and Nanotechnology, Guru Jampeshwar University of Science and Technology, Hisar. First of all, I want to thank to NCIST who has given me the opportunity to share my research idea in front of all of the buddy research scholars. My title of presentation is Synthesis and Electrochemical Study of Zinc, MOF, Reduced Graphene Oxide and Polyaniline for Supercapacitor Electrodes. Next slide, sir. The content in my presentation is because I have given only the 10 minutes to present my research work. So I have brought out mainly what's the capacitor, what's the supercapacitor, and all that's how I have built up the supercapacitor electrode for energy crisis. As you all know that the energy demand is constantly required as there is a lot of energy crisis is there. So by building up the supercapacitor, by making up the superior electrode, one must has to introduce supercapacitor electrode for demands of energy needs. First of all, I have to start from the introduction. Then I want to say that what's the capacitor basically. Capacitor is basically a two-terminal device that can store an electric field. And because capacitor power density is less, that's why the new energy demand, the new research phenomena is supercapacitors. So next slide. Now the question arises, what's the supercapacitor? Why I have chosen this topic for my research purpose? The reason is that because of the demand of to fulfill the demand of energy storage and to improve the energy density, as you all know that the supercapacitor has high power density. A supercapacitor has high power density, and by by improving the supercapacitor electrodes, we can improve their high energy density. As there are several materials which are highly conductive, they can even improve as in energy demands. When you see a lot of research, lot of newspaper, it has new research has been going on basing of the supercapacitor, and it has lots of advantage in electronics and in physics and in other branches to improve the energy needs. So it is an electrochemical capacitor, and by improving its energy density, one can improve high energy density. Next slide, sir. It's what's the history of supercapacitor. Basically, I want to say that the first patent for the supercapacitor was granted in 1957 when Becker and his group developed a carbon coated large surface area current collector as in which H2SO4 is used as an electrolyte, and later on by several research groups like SOYO has provided the new concept regarding the supercapacitors, in which there is a ruthenium oxide film in the presence of H2SO4 as an electrolyte has been used. After that in 1990s and on later on, a lot of research has been done on the supercapacitors, and I will tell you how I have built up the supercapacitor in my research lab. Next slide, sir. In the supercapacitor, basically you need there are basically two type of supercapacitor. One is EDLC, another is pseudocapacitors. So basically, I want to tell what's the phenomenon of supercapacitor is. You need two electrodes. One is anode and one is cathode, and you have to use separator as an electrolyte for that, so that you can have the best packaging of the material. You can have slide have a best packaging, and there should be before in the beginning in supercapacitor we are using the liquid electrolytes, but nowadays because liquid electrolyte there is a lot of problem of leakage of that electrolyte. That's why in superior demands, in superior energy needs, gel electrolyte in today field are being used. In the next slide I have done the animation of how this supercapacitor working is to be taken place. So next slide. Why supercapacitor? Because of specific power, because of high power density. It can, because when we use the battery in general life, it takes lot of time to recharge it again. So by using the supercapacitor, we can get the instant recharging of our electrical devices. It has nowadays high power density of 5000 watt per kilogram has been reached, and it has high superior capability. It has high charging discharging cycle, repetitive charging cycle, high degree of reversibility, and high suitability. Okay, next slide. Here I have shown the comparison between the normal capacitor and a super capacitor. As you are going to see in the normal capacitors, at a same particular DC voltage rating, as you are going to able to see in the screen, that normal capacitor charge up to 26.4 joule, while a super capacitor in the same DC voltage rating charge up to 547 joule. In similar manner, when a normal capacitor charge up to 5.9 millijoule, a similar super capacitor can charge up to 1.5 joule. Okay, so there are a lot of things to be discussed. Now in my presentation and now my research work, I have used metal organic framework, that is MOF. In basically MOF in general, I want to tell you that it is basically a linkage between a metal ions and an organic linker. Because of their high corrosivity, their cage-like structure and the repeating structure and high surface area, their property can be easily tuned because it is composed of both organic and inorganic components. So although it is not so much conductive, but by making its composite, it is very good material for the superior electrodes. Next slide, sir. Here is an animation of MOF I have done. In this, there is a linkage between a metal ions and a organic linker. Organic linker you can select from any of the research paper which have the better linkage with the metal ions. And I have in my research paper, I have used zinc MOF. Although another material can be used, but zinc have the high suitability for the superior electrodes. Next slide, sir. Electrochemical supercapacitor has high important role in the material designing, and MOF are using because of the high power density, good reversibility, high intrinsic safety. As one of the primary research scholar are also listening to my presentation, I want to tell you that if you want to do work on a supercapacitor, first of all you have to select the material with having a high reversibility, high power density, highly conductive nature, large surface area, so that the movement of charge can be easily taken place. Faraday reaction and the separation of the charge between the electrode and electrolyte interface must be clearly passed out, and so that there will be the high power density and high energy density can be achieved. Next slide, sir. Now the question arises, why to use reduced graphene oxide and polyaniline with zinc MOF? I've already tell you that MOF is not so much conductive, but why it's making its composite with another material which are highly conductive and their property can be easily tuned. So in graphene oxide have high good electrical property and have widely investigated over the component of supercapacitor electrodes. Although it has some disadvantages, that it has low specific surface area and it is and the difficult fabrication. But nowadays different type of research by making its composite with different MOFs and different type of polymers, one can make better superior electrodes. In similar manner, polyaniline is a conductive polymer. It has high reversibility, highly specific surface area, electrical conductivity, and it is highly compatible with another MOFs and other carbon-related based materials. So that's why reduced graphene oxide and polyaniline has been widely used for the fabrication of supercapacitor electrodes. Next slide, sir. Now, Okay, in the zinc MOF, it has been. I'm already told you that we can take copper MOF, we can take zinc MOF, but nowadays various report work has been done by the Lin and his co-workers, and it has high cyclic stability, excellent cyclic stability. It has larger capacitance when it is to be induced with carbon-related materials and other polyaniline, other composites. It show highly excellent cyclic stability. The result has been proved from the electrochemical study of these composites. Next slide, sir. Next is You can make the MOF, zinc MOF, has been discussed from the various research paper in the lab. I have made that. I am making the comparison with different type of composites. I have made the Z1, Z2, Z3, and Z4 composites. In G1 composite, all you have to prepare by the co-assembly method, in which you take zinc MOF as in concentration of 0.02 gram and graphene oxide dispersed in a 5 ml distilled water to make a suspension. In G2, you have to just replace the MOF with polyaniline. In third component, you have to take the mixture of all of the three, reduced graphene oxide, polyaniline, and the zinc MOF. After that, final composite G4 is to be made. Okay, so I have made the 4 different composite, and making the such comparison, I want to tell you the mixture, that final composite show better supercapacitance, and they are highly conductive. Their supercapacitance value is very large, show high energy density values. Next slide, sir. It's basically a research method. It's my graphical presence of my abstract. In this, by Hammer's method, we have prepared the reduced graphene oxide by introducing the zinc MOF in it. It is showing hybrid aerogel, and after polymerization, it formed the hybrid composites. So this is a general preview. For the short oral presentation, it is clearly indicating what's the research method I have introduced. On later slide, the characterization for that MOF is to be done by the XRD, FTIR, SAM, BIT. In XRD, you have just to make the crystal structure analysis of zinc MOF can be easily done by the XRD. FTIR provide you the better chemical composition. With ATR technology, you get the related functional group like detection. By the SAM, you get the morphologies, and surface area, specific surface area is easily done by the BET, that is Browner-Emmett-Taylor method, and it show you get the nitrogen adsorption isotherms plot chart to characterize the electrochemical study of superior electrodes. Next slide, sir. And there is a flash method for the determining the amount of each element. You have to evaluate the percentage by weight, and by the flash method, there is some destruction of the material also. So you have to optimize it and packed in a silver capsule that can better result out to avoid your destruction of your material. EDX is another method that is determine energy concentration is to be evaluated based on the X-ray diffraction material. And TGA measured with conductive with a high rate. If you want to know the temperature analysis regarding your material, this will give you the better result about your heating effect. Also, these things can be calculated by TGA analysis. Next slide, sir. This is a sand image of the samples, and you are getting there are different type of SAM composite, SAM images of G1, G2, and G4 materials, and these are the TAM images. Here you get some idea what's the crystalline nature of zinc MOF, and second one is telling what's the composite is, how the composite show the morphologies, and these are some TAM and SAM images of the various samples that is to be analyzed. Next slide, sir. And this is a
kindly hurry up.
Okay, it is a BET analysis of composite material. There you get some idea regarding your surface area analysis. Next slide, sir. That is FTIR spectra of various material, which is showing you the peak of G1, G2, and G3, G4 composites. Next slide, sir. This is a TGA spectra of G1, G2, G3, and G4, and you have it is clearly indicating by the different colors that graph that how you analyze your temperature analysis with your weight percentage. Next slide, sir. This is a preparation of electrode material slurry you have to make with the solution of polytannylthin PTFE, and the slurry is coated over a circle over a titanium mesh. Then you have to compress it, and after that you have to analyze your cyclic voltammetry, galvanostatic charge discharge test. This is a method for the preparation of electrode material. Next slide, sir. This is basically a system in my lab. The analysis of electrochemical workstation is basically this. It is of auto lab. It includes 3 electrode systems which have working electrode, reference electrode, and platinum wire electrodes. This is basically how we take the analysis. Next slide, sir. And this is cyclic voltammetry graphs of G1, G2, G3, G4, all samples at 5 millivolt per second, and at low scanning rate it is showing a area, and after that at high thing it shows us climbed lands. Next slide, sir. These are charge discharge plot of G1, G2, G3 and G4 samples of at different scanning rate from 0.1 Ag to 5 Ag. Next slide, sir. This is electrical impedance spectra in 1 molar H2SO4 with of different charts G1, G2, G3 and G4 samples, which I've already discussed what are the samples, and there are different type. In one sample we have taken reduced graphene oxide with polyaniline, in one sample we have taken zinc MOF with polyaniline. So these are some graphs. Next slide, sir. These are two electrode capacitance. I have taken cyclic voltammetry charge discharge plots at different rates. Next slide, sir. At 5 millivolt per second. Next slide, sir. This is a cyclic capacitance retentivity at different cycles from from 1000 to 5000, different cycle, different frequency rate with capacitance retention. These are some plots. Next slides. Okay, as lot of buddy research scholar who have finally started the work and wants to do work on the supercapacitor, they can use different MOFs, different type of composites. Sir, I have, can I get 3 to 4 minutes for speaking further on conclusion and future remarks?
Sorry, ma'am, we have running out of time, so kindly shortlist.
Okay. Okay. Thank you, sir. Actually, I have the primary research scholar can build up the good research in the area of supercapacitors. They can build various MOFs. They can build up the various composites. By fabrication of that composite, it can be a good research. You can take the various CNTs. You can take the material which are conductive in nature. By making the composite with MOFs, it can be a better good research. Next slide, sir. Okay, in the final conclusion, you have to introduce the main area, the main part of this conference is only that key. You all the search scholar must understood how you take suitable material. You have to for the supercapacitor, you have to take the conductive material. You have to consider the material which have highly interfacial, which is highly stable, which have a proper specific area, which have proper highly stable, which have a good charge discharge cycle ratios. These are the main point which I want to indicate before you start your work as in the field of supercapacitor. Next slide, sir. Okay, and you have to consider, you have to take the novel materials by attaching the MOFs with conductive nature, and by studying the important property of MOFs. You can take various MOFs, zinc MOF and other ones are the good one to introduce your research work. Next slide. I think so it is closed. Thank you, everyone. If there can be any discussion, I am ready to.
Thank you, ma'am. It's a nice presentation. It's an open section for the audience. If anybody have doubts, you can raise your voice.
Priyanka, I have some few questions. So
yes, sir.
Why did you choose zinc MOF? Because this is not conductive, right? So why did you choose zinc MOF? And what is the purpose? Yeah. And which linker are you using for zinc MOF?
Okay, so zinc MOF, actually the lot of Lynn and its co-workers I've already mentioned in my presentation also. Zinc MOF it can be easily compatible with the other composites. As lot of research has been done, I've already told. I have used, first of all, I have to say, I used terephthalate acid as an organic linker with zinc MOF, and it is easily compatible with other composites and other carbon-based materials. A lot of research has been done, and zinc is most compatible material. Zinc is most compatible material with linkage with other materials like carbon-based material. I have taken reduced graphene oxide. And what's next question you have asked, sir?
What's about that solubility or dispersibility of your zinc MOF with your reduced graphene oxide and other naponi?
Okay.
Is it soluble or it is dispersed, and how you measure?
Okay, sir, it is already in the research, lot of research has already done on the compatibility of the zinc morph with other polyaniline. It is showing a good results and showing the result of specific capacitance of 372, which is the largest one in the 2021. Although I have not published my research work in anywhere, it is generally submit my abstract here, but a lot of compatibility for the body research scholars who are primarily doing their work. They can easily make their morphs with, instead of using reduced graphene oxide, they can use carbon nanotubes, CNTs, and another one are the good aspects for the research work.
Okay. So do you think you are talking about the compatibility, right? So can you explain what kind of interactions, chemical interaction in the system of zinc morph with your Pani and reduced graphene oxide?
Okay. Sir, it's compatibility. If I want to clear it out, then it is means that when you introduce your zinc morph, because morph are less conductive, but because of the highly tunability, when you prepare using morph, it is easily interact with the other carbon-based material. If in a short term, in a simple way, if I want to told you, then it is means that generally those simple morphs are there, they are less conductive, but zinc morph when interact with carbon based material, it shows the electrostatic interaction, and there is a total pathway when we calculate the value of specific capacitance, another charging discharging cycle, where I've shown a lot of graphs in my research, in my presentation. It's are showing a good one results.
Okay, so did you record for your XRD composite? For your composite, did you record XRD for your composite before and after the process?
Sir, actually, I have already told you that I have never submit my this paper for any kind of research. I have just shown my research work in the abstract given to only to this conference. I have never submit my paper to any journal right now.
Okay.
So the result which I have taken out, I have shown in this my presentation.
Okay.
This is the only medium which I have told my this paper. Actually, I am also a primary research scholar.
Okay, so that's all from my side. If anybody have a question.
And one more question. Amada Ishwaran, can you please raise? Amada Ishwaran. And I have one question. And what is super capacity?
Sir, I'm sorry to say, but I'm not able to listen you. What are you saying?
What is super capacity? Super capacity.
What is super?
Capacity. Super
Sir,
capacity.
Super capacity.
Do you know what is
Sir.
super capacity? It
The
is
word
related.
is super capacity.
Yes, it is the word related to super capacitor. You are working in super capacitor, right?
Yes, yes.
So you know super capacity.
Sir, super capacity, I think so. No, I have no idea, but I will see in various research paper. I definitely at particular moment I've never read about that. I have generally studied about the charging, discharging, and other simple manners.
Okay.
But very nice question. I must read out it.
Okay.
Yeah. Thank you, ma'am. So thank you for your presentation.
Thank you very much. Again, I am thankful to NCIST for presenting my research work and on all the various type of scientists and the superior research scholars. Thank you very much.
Next presenter is NT55.
Yes, sir.
And followed by NT55. NT17 should be ready for the next presentation.
Am I audible, sir?
Yeah, it's fine, ma'am.
Shall I present now, sir?
Yeah, just a second. I will share the presentations. Yeah. Yes, you can start, ma'am. Kindly stick on the time so that we can give option for the other presenter to complete the presentation on time. Yeah, you can start now, ma'am.
Our honorable and eminent judges, diligent and dedicated professors, and ambitious students, a very pleasant good afternoon to one and all. I am S. Lashma, first year BSc Physics student. It is a great honor to share a few words about the recent advances in nanomaterials and their applications in this inspiring and motivational national conference. Nanotechnology is the new frontier of this century, which has grown globally into an industry worth trillions of dollars. Next slide. Welcome to the nano world. Physics is the fundamental of all science. And nanotechnology, sir, previous slide, sir. Welcome to the nano world. Physics is the fundamental of all science. And nanotechnology is a miracle of science, which is revolutionizing medicine, defense, food safety, energy, electronics, environmental science, etc. Next slide, sir. Nanomaterials, which are the pillars of nanotechnology, have at least one dimension less than 100 nanometers. 1 nanometer is 1/1,000,000th of a millimeter. Next slide, sir. The world's first nanoscience-based product was made in 600 BC in South India, and its evidence was found at Kiradi in Tamil Nadu. Next slide, sir. Micro-Raman spectrum of the inner black coating shows the presence of carbon nanotubes. Next slide, sir. And the TEM analysis also confirms this. Next slide, sir. Materials reduced to nanoscale suddenly show extraordinarily amazing properties. For example, gold nanoparticles are red, purple, blue, or even green in color. Next slide, sir. Smaller is cheaper, lighter, faster, and smarter. Graphene is 200 times stronger than steel while weighing less than a paper. This miracle material has countless applications. It is 150 times more conductive than silicon, and it can lead to charging a smartphone in seconds or an electric car in minutes. Next slide, sir. Researchers have made a highly sensitive COVID-19 detector using graphene just before 2 weeks. In this detector, the frequency of the phonons, that is the resonant vibration of the antibody-coupled graphene sheet, changes when treated with a COVID positive sample, which is measured by a Raman spectrometer. This fast and inexpensive detector will help in the detection of coronavirus quickly and accurately in less than 5 minutes. Next slide, sir. The ongoing quest for miniaturization has resulted in tools like the atomic force microscope. Next slide, sir. The scanning tunneling microscope. And next slide, sir. The electron beam lithography. Next slide. Which helps the researchers manipulate and manufacture nanostructures now. The unique quantum and the surface phenomena at the nanoscale give rise to new materials and revolutionizing applications such as, next slide, sir, targeted drug delivery to kill cancer cells without affecting the normal cells. Next slide, sir. Ultra-sensitive biosensors to diagnose diseases. Next slide, sir. Tissue engineering, which can replace organ transplant. Next slide, sir. Gene repair and precise surgeries using nanobots. Next slide, sir. And cost-effective nanosensors to detect air pollutants, food contaminants, and even bombs and drugs. Next slide, sir. Cystic fibrosis is a genetic disease that causes chronic lung infections leading to lung failure and needs lifelong antibiotic therapy. Next slide, sir. Here in row 1, after 4 hours, if the infection is not treated, it kills all the cells. In row 2, tobramycin keeps the cells alive, but it does not eradicate the infection. In row 3, by enhancing the tobramycin with the lipid liquid crystal nanoparticles, its effectiveness was improved by 1 lakh times, and it eradicates the infection in as little as 2 doses. Next slide, sir. Plaque, that is the dead and sick cells, clogging the arteries causes heart attacks and strokes, which are the world's #1 killers. Drug-coated carbon nanotube stimulate our immune cells to selectively eat plaque and save both our lives and money. Next slide, sir. Painful and very expensive eye surgeries with a high risk of infection is being replaced by eye drops with nanoparticles, which is quick, safe, painless, and 90% cheaper. Next slide, sir. Now, a nano needle pokes a living cell and detects the sign of early DNA damage that can lead to cancer. Next slide, sir. The nanoparticle-based COVID-19 vaccine gives greater immunity and is a great step against this pandemic. This nanotechnology reduces the cost and improves the quality of medical technology. It will give promising solutions to various chronic and fatal diseases. Next slide, sir. And will have a major impact on the survival of human race. Next, previous slide, sir. Nanotechnology has fueled the core innovation in electronics and in energy and has led to ultra long life batteries, cheaper and more efficient solar panels, etc. Cheaper, faster, and more efficient nano chips are replacing silicon chips. Next slide, sir. Researchers recently, the armchair type graphene nano ribbon was found to have remarkably strong optical response, which has lot of applications in nanophotonics. Next slide, sir.
Stan, kindly hurry up.
Researchers have made the egg cotton quantum dot array, which contains quantum dots arranged like an egg cotton just before 3 months. It is made of new 2D semiconductors, tungsten diselenide and molybdenum diselenide placed in between two mirrors. When the red laser light is passed through it, the quantum egg cotton captures and releases photons supporting excited quantum states while it possesses the extra energy which can lead to ultra low power devices. Next slide, sir. Previous slide, sir.
It's time, kindly conclude.
It can bring quantum devices up to room temperature rather than extreme cold of liquid nitrogen or helium and can lead us to land beyond silicon, which produces more heat. Now it is the dawning of nano age. Next slide, sir. Next slide, sir. Next, sir. Next slide, sir. Now it is the dawning of nano age after the silicon age. Nano revolution has improved our standard of living with more than 2,000 products, longer lasting satellites, stain-proof clothing, incredibly powerful computers, 4D printing, life-saving medical devices, zero pollution manufacturing, self-healing ageless materials, biodegradable plastics, or some astonishing applications set to change the way we live. The future belongs to nanomaterials, which could provide efficient, cost-effective, and eco-friendly solutions to the global challenges. So let us try to reveal many more mysteries of this microscopic universe to attain nanotechnological advancements that will meet the urgent technological demands for achieving a sustainable and safe society. So let us make our India a superpower and save our earth through nanotechnology. Thank you for this wonderful opportunity. Thank you, sir.
Okay. Am I audible?
Yes, sir, you can ask.
What the first year?
First year BSc Physics students.
Okay, okay. Nice presentation, Ma. And can I say what is the different colors of gold?
Red, purple, blue, or even green in colors.
Okay. And what color of gold is most expensive? Do you know what color of gold is most expensive? I can ask only basic question because of you are a first year BSc student, so that's why.
Green, maybe, sir.
What?
Green, sir.
Green.
I don't know, sir.
Okay. Okay. Difference between nanoscience and nanotechnology. Can you say the difference between nanoscience and nanotechnology?
Nanotechnology
It is
is
a basic question.
technology conducted at about 1 to 100 nanometers.
Nanotechnology. Okay. What is meant by nanoscience?
Nanoscience deals with nanomaterials and nanoparticles.
Okay, no problem. You can read that. What is the difference between nanoscience and nanotechnology? Okay.
Okay, sir.
Okay, no problem. Nice presentation, ma.
Thank you, sir.
Next, dear participants, you can ask any queries. Please raise. Otherwise, you can go for next.
Yeah, I have one question connecting to the previous one. So you are observing a change in color, right?
Yes.
What is the science exactly? Why there is a color change we are observing in gold nanoparticle with a different particle size, right? Can you?
Because
Yeah.
it reduces its sizes reduces
Okay.
to quantum level.
Okay.
Due to quantum effects.
Mm-hmm. Did
So
you
color
know
changes.
about some phonon scattering kind of thing?
No,
Did you go through?
optical property
Yeah.
changes.
With respect to the size. Okay. And you mentioned about nano vaccine.
Yes.
So in future, you want to make nano vaccine for COVID?
Yes,
Because you are more interested in COVID. That's why I'm asking this question.
yes, sir.
Okay. Wish you all the best. Yeah.
Thank you, sir.
Yeah, thank you. Really, it's a very colorful presentation. Thank you, ma'am.
Thank you, sir.
Now it's time to present NT17. Amuda is there? Amuda? So Amuda, so I think you will get the notification for unmute your mic. Amuda, you can speak now. So next, NT23.
Shall I start?
Yes, you can start, ma'am.
Okay, sir. Thank you. I am Amuda, research scholar from Manamanim Sunar University, Tirunelveli. My research topic is
Yes, you can continue, ma'am.
yes, sir. My research topic is green synthesis and characterization of lanthanum oxide nanoparticles using Eclipta prostata and its antibacterial activity. Eclipta prostata is an plant, is the Tamil name of Karisalangani.
Ma'am, is it audible to you?
Yes, sir.
Yeah, we didn't receive your voice.
Oh, okay, sir. Some network issues, sir.
Yeah, kindly.
Nanotechnology means is an art of science of manipulating matter is at the nanoscale. So nanoscience is a theoretical study. Nanotechnology is an applied of nanoscience. So nanoparticles having at least one dimension in the range of 1 to 100 nanometers. So various nanoparticles is an example of atom is in 0.1 nanometer. So protein is a 10 nanometer. DNA is a 2.5 nanometer is the one of the example of nanostructure materials. Next slide, sir. Various nanosynthesis methods are used to synthesize the nanoparticles. For example, physical method, chemical and biological method. So particularly I am choosing this biological synthesis method to synthesize the lanthanum oxide nanoparticles. For example, bacteria, fungi, and plant extracts are used to reduce the nanoparticles. Biological synthesis is the rapid synthesis, controlled toxicity levels, controlling on science characteristics. So I am choosing economically is a friendly approaches. So I am choosing the green synthesis method. So green synthesis of lanthanum oxide nanoparticles is used for many applications. For example, MR imaging, biosensors, and LED imaging. So first, mainly lanthanum oxide nanoparticles for fuel cell application. Okay. Next slide, sir.
I think your audio is not, your voice is not audible.
Some network is not here, sir.
Now it is okay.
Methodology.
Yes, you can continue.
Methodology. Fresh leaf of Eucalyptus protostrata was collected from the local area of Tirunelveli. The fresh leaf was washed with multiple times distilled water. Then 5 grams of leaves were taken and boiled with 100 ml deionized water at 80 degrees Celsius for 30 minutes. Then the extract was filtered with using Wattman filter paper. Then the filter rate was stored at 40 degrees Celsius for further use. Then synthesis of lanthanum oxide nanoparticles. So lanthanum nitrate is used as the precursor for synthesis of lanthanum oxide nanoparticles. 1 millimolar concentration lanthanum nitrate solution was taken, then added the 20 ml of leaf extract was added into this solution. The resultant mixture, the stirring used the magnetic stirrer for 30 minutes. Then the formation of intense pale yellow color solution was confirmed the lanthanum oxide nanoparticles. Then the solution mixture was centrifugation for use the centrifuge at 6000 rpm at 20 minutes. Then the nanoparticles was finally dried for a hot air oven 80 degrees Celsius for 3 hours and then calcinated for 400 degrees Celsius using muffle furnace. Then the characterization of lanthanum oxide nanoparticles used a varied characterization. For example, UV spectroscopy, TEM analysis, SEM, and particle size analysis. This image shows X-ray diffraction study of lanthanum oxide nanoparticles. XRD is analysis used to measure the crystalline structure of nanoparticles. The crystalline nature of biosynthesis lanthanum oxide nanoparticles was shown in figure. The diffraction peaks corresponding range of 001 plane, 002, 102, 211 plane crystalline planes are shown in the lanthanum oxide nanoparticles. So XRD pattern was confirmed the formation of hexagonal structure using JCPDS core number 050602. The crystalline structure of lanthanum oxide nanoparticle was calculated 32 nanometer using Debye-Skinner formula D equal to S lambda by beta cos theta. Then next figure shows the UV spectroscopy. UV is used to measure the wavelength range of nanoparticles. The lanthanum oxide nanoparticle wavelength is 260 and 320 nanometer range. Then next image is shown in some scanning electron microscopy. Scanning electron microscopy is mostly used to measure the shape and sizes of nanoparticles. Some microscope of lanthanum oxide nanoparticles is mostly hexagonal and remaining particles were rectangular rod and spherical and undefined shape. If this image shows FTR spectrum of lanthanum oxide nanoparticles. So FTR is mostly used to measure the functional group and functional group of lanthanum oxide nanoparticles. So this image, the functional group of 3,450 centimeter is a stretching vibration of water molecules. Then 2,221 centimeter power -1 is the vibrational ranging of CN stretching to remove the nitrile compounds. Then particle size analyzer. Particle size analyzer is used to measure the particle size. This is at 20 nanometer. Then antimicrobial activity. The synthesized lanthanum oxide nanoparticles was used to perform agar-well diffusion method against the bacterial strains Staphylococcus, Bacillus, Enterobacter, and Pseudomonas.
Ma'am, again, it is not audible.
Antibacterial activity. The pathogenic bacteria was grown into nutrient broth for 24 hours. Culture of these strains was swabbed uniformly onto these individual plates containing molar Hinton agar was using to sterile cotton swabs. Then the concentration of lanthanum oxide nanoparticles at different concentration 25 μl, 50, 75, and 100 μl added into each plate. Then the plate was incubated for 24 hours at 30 degrees Celsius. After the incubation levels, at different levels, the zone of formation was around the well was measured.
Okay, thank you, Amada ma'am.
I have a question. It is audible?
Yes, sir. For us, it is audible. I think it's not audible for the Amada ma'am.
Oh, okay. No problem.
So we move on to the next sections.
Okay. Yeah.
Now it's NT20. Prashant Kumar is there?
Hello.
Yeah, hello.
Yeah. Hello,
Yeah,
sir. I am.
you can start now.
Good afternoon to everyone. Myself, Prashant Kumar. I am working under the area of magnetic nanofluids under the supervision of Dr. R.P. Pant, SCSR National Physical Laboratory. And today I have delivered my research work in the area of enhanced electromagnetic optical property stability of cobalt dope mixed nanoferides for nanomagnetic fluids. Second slide. Yeah, these are the outline of my research work, motivation, introductions about mixed ferrite nanofluids, synthesis methods, result and discussion, conclusion. Next slide. Motivations. These are my I'm working in the area of magnetic fluid. Magnetic fluid are a smart material having sensational acceleration property by changing their shape, size, viscosity, dimension by applying a magnetic field. So it development very important. The magnetic mixed ferrite based nanomagnetic fluid are synthesized by tuning their shape, size, and like also parameter like shape, size, distribution, magnetization, and Curie temperatures. Ferrite space magnetic fluids have various applications in the area of various magnetic in the area of various field like damper, magnetic bearing, energy conversion, and coolants. Next slide. Yeah, introduction of magnetic field. Magnetic field are consisted of collateral magnetic nanoparticle whose size is 2 to 10 nanometer, suspended in stable carrier medium. Particle align in direction of magnetic field. There are variety of applications. They are biomedical, hypothermia, damping, sealing, and cool sensor and switching. And these are the unique property about the magnetic fields. They are to magnet 3D shape, move to hold direction when we apply the magnetic field. These are the pictorial presentation about the magnetic nanoparticle, and they are the surfactant attached on the surface of nanoparticles. Next slide. Magnetic particle and magnetic fluids. Magnetic particle consist of magnetic fluids, and they are the picture which represent the magnetic nanofluid and surfactant layer coated on the surface of nanoparticles whose size is 2 nanometer, and these are the various particle size depending on the various applications depending on their size. In ferrofluid, we are working in the area of ferrofluid. These are used in sealing, damper, sensor, energy devices, and these are the various magnetic nanofluids are prepared in our lab. So basically, we have discussed about the fluid stability. Fluid stability depends upon the bounding motion from particles, components to the gravitational magnetic force. Surfactant also play a very important role in case of magnetic nanofluids. These are the oleic acid as generally used for agglomeration of nanoparticle. Coagulation by the providing steering repulsion among the nanoparticles. Second slide. Next. Introduction of the ferrites. Ferrites are the cubical Spanish structure AB2 family. They are the cubic structure occupy the tetrahedral and octahedral sites like oxygen ion in FC position, cation and 64 atom per unit cells, whose octahedral sites are occupied 30 unit 2 per unit cells, and other are occupied by 8 and occupy iron ions, other iron 2 positive and 3 ion by simultaneously. Site occupancy determined by the element oxidation state. Fabrication also, these are the crystal structure of tetrahedral and octahedral sites whose occupancy is given as per the site of occupancy of the each atom and ions. Next slide. The other my synthesis method we adopt in my today research work by using the chemical composition method. We synthesize magnetic nanofluid and take three salts mix with each other, further added ammonia, then distributed in a foam, further dispersion in kerosene as a medium, and finally we obtain the single surfactant coated cobalt doped nanoparticles kerosene based dispersion and fluids. Next. These are my and discussion of my work. Further, we have prepared nanoparticles. Firstly, we are characterized by the XRD. XRD, we find the various parameters like crystalline size, lattice parameter, volume density, and other parameters also. And these spectra also so that each plane corresponding to each plane by the diffraction pattern, and these are the ritual refinement which were done by the professor pair, and also the confirmed by cubical spinal phase of each lattice plane corresponding to the Black's angle. And next slide. These are my crystal structure of cobalt structure and each atom occupy each tetrahedron of the sites, and they are the variation lattice parameter along with the crystallized size with the cobalt concentration. When we increase the cobalt concentration size and also increase also lattice parameter increase. These are the Hoping lengths. Hoping lengths means they are the distance between the cations and oxygen ions. These are also increase the cobalt concentration. Next slide. These are the parameter we find by the XRD. We are the like crystal size, particle size, lattice strain, volume, X-ray density, Hoping length, and these parameter we find out from the XRD spectra.
Is it audible?
No, sir.
No, sir. Prashant Kumar? Prashant Kumar is available? Hello, sir. Can you hear me? Prashant Kumar.
Hello, sir. Are you audible?
Yeah.
Yeah. Can you share my screen?
Yes, go to the conclusion slide, please.
Yes, sir.
Already time is over.
Okay, sir.
Go to the conclusion.
So in this study, we have prepared cobalt dope and iron ferrites by the chemical methods. And oleic acid was used and primary surfactant to avoid the aluminum nanoparticle. These prepared nanofluid are and details such to study how done by cubical surface phase, and no impurity was observed, and the crystalline size will also increase the cobalt concentration. That is parameter will also find good agreement with standard cobalt flights, and the cation distribution, and it will define also were quoted by the DC magnetic measurement, which we significant more regarding about the enhance the magnetic property to optimize the cobalt dope sample. FTR and UV visible spectra also will and these vary from 3.1 to 3.8 nanometer increase the cobalt content. The magnetic property was also a little bit room temperature DC magnetic measurement, whose corrosivity also vary from 26 to 61, and also the magnetic property. These magnetic particles show supermagnetic behavior with low corrosivity, and these nanoparticles have excellent stability. Various used in various field like magnetic storage data, memory devices, optical fiber, and magnetic fluid hyperthermia. Thank you, sir.
Okay.
Yes, sir.
Finally, you can conclude that the band gap increases with
Yes, sir.
the how the band gap increases from 3.1 to 3.8 electron volt.
Yeah. So we have calculated by the Taubros method now. So these when increase the cobalt concentration, they increase with 3.1 to 3.8 nanometer electrovolt with increase the cobalt concentration, which we have calculated from the Taubros method.
So please go to the characterization slide.
Yeah.
Back. Back slide. Back starting slide. Yes, next. Wait. Here,
Yeah.
decondition was in centrifugation.
Yeah,
Here you
yeah.
can 10,000 RPM for
Yeah,
12
yeah.
minutes. How you can
Yeah.
fix 10,000 RPM?
By using the and then centrifuge instrument, in our lab, we have manually fixed by an exact 10,000 RPM for also in 12 minutes by using centrifuge instrument by Remy made.
Suppose we can reduce the RPM, what will
Yeah.
happen?
Actually, we have which we have mainly we required a fine size particle. Fine means about 10 nanometer. When we decrease the RPM, and the particle are not homogenized, not and also not distinct, means that not form homogenized particle. Finally, it means the particle are not in uniformly distributed around this.
Go to the next slide. Here, red
Yeah.
field refinement.
Yes, sir.
X-axis is unit,
Yes, sir.
What is the x-axis unit? You can put 2 theta na? In bracket.
In
What?
degree, yes, sir. Degree. This is mentioned symbol degree.
Degree. Okay.
Yeah.
Okay. Thank you. Anybody's asked queries? Please raise.
Yeah. Yeah. So first question is, so why are you using kerosene?
Yeah, actually, in my nanomagnetic fluid, basically we are working in the area of nanomagnetic fluid, and these firstly we have developed a nanoparticle, then and coated with in a stable material like oleic acid and other also surfactant, and these surfactant in dispersed in a stable medium like kerosene, water, paraffin, etc. to obtain a stable nanomagnetic fluid.
Okay.
Yes, sir.
Another question. So you done retold refinement by
Yes,
yourself
sir.
or it's a
No,
collaboration?
I have also done myself by using the.
Okay.
Yes, sir.
So when we are doing retold refinement, you have to mention on value, right? What is that value? When you are doing retold refinement,
Yes, sir.
you're supposed to mention on value. What is that value?
Which value, sir? Which value? Which one?
R value. R value. R value.
Yeah, we have obtained
That will
various parameters.
shows that.
Yeah, yeah. Yes, sir.
Yeah.
We have obtained various parameter by the refinement.
No, that R value.
Actually, we have obtained, but in slide are not mentioned. We to find out from these different value like RW and R experimental, yeah, different chi-square also. Then also ladies, these are the volume unit cells. Various parameter we have find, but in slides I will not mention.
Okay.
Yes, sir.
Because at least you mentioned the R value, that is better to understand how it is fitted to in your things.
Okay, sir. Okay, sir. I will mention early.
Okay, is interesting. Good.
Okay.
And yeah, that's all from me, sir.
Okay, sir. Okay, thank you, sir. Thank you so much.
Okay.
Next, I will call on NT23, Mr. S. Selvakumar.
Good afternoon, sir.
Yeah, good afternoon, sir. Just a minute, I will share your screen. Yeah, let's start, sir.
Good afternoon, everyone. I am Selva Kumar. Sir, I am audible?
Yeah, audible, sir.
Okay, thank you. So I am
Sorry.
Professor, Department of Renewable Energy Science, Manamustana University. My research entails is enhancing the thermal performance of basically solar energy or photovoltaic, and light energy is converted into thermal part. So my research field is the second part. Light energy is converted into heat energy. So solar energy has fitted into a lot of solar cooking system, solar drying system, and solar water heaters and solar irrigators, solar desalination system. So solar collector, it is the central component of any solar thermal device. It absorbs incoming solar radiations converted into heat and heat for thermal applications. But my improvement in performance in solar collector, integrating heat transfer configurations in solar collector, the performance of solar collector can be improved. So objectives of my research study, preparations of nanostructure absorber, development of solar collector with the nanostructure absorber, and thermal characteristics, and also experimental assessment of the performance of solar collector with nanostructured observer configuration. This is totally entirely experimental study for daytime 9 to 4 o'clock. So first, let us move the first objective 1 preparations of the nanostructure absorber. So nano-sized carbon and nano-sized aluminum carbide prepared by ball milling method. Nano-sized carbon and aluminum carbide were mixed up with black emulsions in different ratios. The solar emulsions available in market. So and resultant solutions was coated on pre-cleaned copper substrate by spray coating method. Sample absorber was characterized through XRD analysis in the confirmed nanoparticles. So
Sir, please unmute, sir. Selvakumar, sir. Sorry. Yeah, continue. Sir.
Okay, sir. Next slide, sir.
I think the screen is not moving.
It's moving, sir.
Yeah, it is moving.
Yeah, it's moving, sir.
No, for us, we are seeing only that solar collector improvement.
Okay, okay. One more time I will share, sir. Now it's visible, sir?
Yeah, now it's okay.
Please. Selvakumar, sir.
Sir, shall I continue?
Yeah.
Continue, sir.
Selvakumar, yes, you can continue your presentation.
Sir, shall I
Yes, sir, you continue, sir.
continue?
Yeah. You continue.
Sir. So first objective, nano-sized carbon and nano. So solar emulsions available in solar market. Then sample observer characterized through XRD analysis is only confirmed for the nanoparticle size. Next step.
Sir, your voice is not audible, sir. Selvakumar, sir. Karthik, sir.
Yeah. His audio is
problems.
His voice is
issue,
not
maybe.
audible.
Okay. Anyway. Selvakumar, sir. Please respond, sir.
Okay, sir. Sir, 80. Sir, I'm audible, sir?
Yes.
Yeah, yes. Please.
Sir, discontinue. Again, discontinue. Okay, sir. These are the nanostructure observable plates for different ratios, 80-20 and 70-30, 60-40, and molar ratios for nanocarbon and nano aluminum carbide. Next slide, sir. Okay, these are the ball milling method, bituminous coal and hammering, using hammering and using ball milling method, particles of grain size, and also grain in the particle aluminum carbide and bituminous coal carbon. Next slide, sir. These are the 10 to 10 centimeter length and breadth. So 80-20 nanocarbon and nano aluminum carbide, 70-30 and 60-40 and molar ratios for nanocarbon and nano aluminum carbide. Next, sir. So these are the XRD studies revealed that the coating had the crystallite in nano ranges. The crystallite size was 52 nanometer. Next slide, sir.
Sivakumar sir.
So these are the prepared observer plate was integrated subsequently in solar collector. So design and development were as per standard.
Sir, actually slide is not moving. Kindly check.
Here is no issue.
Sorry,
Screen is
sir,
moving,
again
sir.
disconnected.
Sir, now it's
And now also the same problem.
the same. Screen is
Yes.
not visible, sir.
It is visible, but it is not changed. It is not moving.
It's not moving, yeah.
Yes.
Yes, sir.
Okay, but you are changing, sir.
Sir, I think I concluded.
Yeah, just.
Sorry, sir. Actually, I concluded that improve the thermal performance of solar collector. So now I improvement the new designing for honeycomb structure and spherical structure using different nano coating, this types of material. We can improve the thermal efficiency of solar thermal collecting system. That's all.
How much percentage
you,
you can do?
Sir, 72.5%. Now this
how
research, aluminium carbide and bituminous coal.
Okay. Now at present, how much efficiency percent?
Using also theoretical prediction.
Kumar, I am not audible.
But the experimental is 2 to 5%.
Okay. Do you know our,
Sorry, sir?
our that? Okay, no problem. Do you know our of that transparent solar panel? How do you make?
No, sir. No, sir. Now I am only in the field of solar thermal. Light energy is converted to heat energy. So heating applications only. So using heat energy is converted to applied in electrical energy is not my field.
Okay, no problem. And one of the transparent solar cell is also available. Okay, no problem. Thank you.
Of the solar irrigating solar system and solar drying system.
Okay, pa. Okay, pa. That's all said.
Okay, sir. Thank you, sir.
The participants, thanks for your presentation. It's time to say warm words of thank you to our beloved judges. Dr. R. Karthik, Advanced Scientist, Momentio Performance Materials, Bangalore. And Dr. J. Tirupati, Assistant Professor, Kalpagam University, Coimbatore. And Dr. M. Manivanan, Head of the Department of Physics, Pachamuthu College of Women, Dharmapuri. Thank you, judges, for spending your valuable time. And thank you, my dear participants. The next technical section will be took place after 5 minutes of break. Please. The next section will be took place at 3:40 p.m.
Excuse me, sir. Good afternoon. May I know this oral presentation about the CG just to growth?
Yes, sir. The oral section will be took place after 4:30. We will be continuing after 4:30. After the third technical session, the oral section will be continued. Please hold on.
Thank you, sir. Thanks for your invitation. And it's my pleasure. I just want to add one comment, few comments about the thing about your presentation, students' presentation. So when
Yes.
you are giving presentation, you don't pronounce sem, tem kind of things. Even research scholars are using these terms. And I noticed that BSc Physics first year student, he correctly said SEM, TEM like that. So you should not pronounce sem, tem like that. So scholars, please remember, it is a scanning electron microscopy. It is not a word, right? It is an acronym, SEM. So when you are presenting, use the thing SEM, TEM like that. Don't use sem, tem. Okay, this is one thing. And when you are presenting, don't rush. Okay, you just present whatever you want to discuss. You can clearly explain it. No need to rush. This is the second thing. And the third thing which I noticed is, even in research scholars, I found that if you are writing any chemical formula, it should be properly written. You should not write capital letter all the things, right? Formula and all. If you are writing lanthanum oxide La2O3 means you have to mention La2O3. You cannot simplify it like LaO. And even in your title itself, I observed that L capital A. So A should not be capital, right? When you're writing a formula, especially chemical formula, please make sure about the superscript, subscript, and everything you have to be taken into consider. Okay. Yeah.
Sir, thank you, sir. Thank you so much for your valuable comments. Scholars will follow the feature. Okay, next, sir, Brito, sir.
Yes.
Hi, okay, sir. Sir, Chugrit.
Yes, I'm here.
Okay, sir. Then we will start after 2-3 minutes.
Okay, sure. Thank you.
No, for control. Sir, Brito, sir, let's start, sir. Brito, sir.
Yes. Hello. Yes, sir. Now we are entering into the third technical section of this NCIST. I now request Dr. S.A. Martin Vittodas, Assistant Professor, Department of Physics, to introduce this speaker. Welcome, sir.
Good afternoon. Here I am to introduce Dr. Subhadip Chakravarti. It's my privilege to introduce Dr. Subhadip Chakravarti for this national conference. At this juncture, I would like to thank the organizing committee, especially the convener, Dr. Saranraj, for giving this opportunity. I know Dr. Subhadeep for more than 10 years. He's a molecular spectroscopist and currently venturing the world of astronomy with the aid of spectroscopy. He completed his postgraduate degree in chemistry from Indian Institute of Engineering, Science and Technology, Kolkata. Then he joined in IISc Bangalore for his doctoral degree. Since 2015, he is working as postdoctoral fellow in different institutes, including India and France. Currently, he is a postdoctoral fellow in Department of Molecular Physics, Rennes University, France. Though he born in a small village in West Bengal, he traveled from north to south of India for academic purpose, as well as he's traveling throughout the world for his venture. He has published a number of research articles in internationally reputed journals and presented his findings in various international forums. He's a very good chemist and physicist. He's good at solving the physics problems, though basically he's a chemist. The way he explains the concepts of physics is really admirable. I hope everybody will enjoy his presentation. With this brief introduction, I invite Dr. Subhadeep Chakravarti to deliver his lecture. Dr. Subhadeep, the floor is now for you, open for you. Thank you.
Thank you, Brito, for this nice introduction. So first of all, I would like to share my screen. So just 1 minute. Here it is. Okay. So thank you, the organizers for giving me the opportunity to present my research work here. Today, I'll be talking about a relatively new area of research. Am I audible and my screen is visible to everyone? If anyone can tell, just that's enough.
Yes, it is okay. It is visible.
Okay, fine, no problem. Thank you. So so a relatively new area of research, which is the astrochemistry. So basically a laboratory astrochemistry, where we will be I will show you the results from the laboratory experiments and theory and how they can be used to understand the fascinating world of astronomy. So that is what the astrochemistry is all about. And so first of all, just this is a brief outline of my presentation. So where I will talk about the molecular universe briefly, and especially my talk is based on large carbonaceous compounds like polyaromatic hydrocarbons and fluorine in space. And then the signature of these polyaromatic hydrocarbons has been identified in space through the aromatic infrared bands, which I'm going to explain you in a couple of minutes. And also the emission features from fluorine and how infrared spectroscopy can be used to understand or is a better understanding of the aromatic infrared bands and how the fluorine emission bands in different astronomical environment can be explained with the help of the spectroscopy. And finally, another interesting area of research, which I'm relatively new, but I have started since 2 years now. So this is about the evolution of interstellar dust with shocks, and how interstellar dust analogs can be analyzed with the shock wave and the production of the new molecules and all these things. So here, what is astrochemistry? As I just told you, it's a strong consortium between the astronomy, molecular physics, and chemistry. And what we study here is the identification, formation, and evolution of chemical species in the astronomical environment, and subsequently we study the dynamics and the evolution of astronomical objects. So as you can see, it's a kind of, it's a interdisciplinary subject. So it requires the strong knowledge. It's a cooperative effect of the astronomer, physicist, chemist. Everybody has to work together to get some idea about the fascinating world of astronomy. So our universe is molecular, and in 2010, I can show you here, there were 218 molecules have been identified in the interstellar medium or on the circumstellar shells. And most of the identification is done via terahertz region or the rotation, I mean, basically their rotational spectrum, because that's the one which can help or which can tell that, okay, this molecule is present or that molecule is present. So unambiguous identification of the molecule can be done with the help of rotational spectroscopy. And it was in 2020. And 218 molecules were identified. And in 2021, you can see the number of molecules has again increased. So 218 to 250 molecules have been identified. And the molecules are also two atoms, starting from 2 atoms up to more than 12 atoms. And most interestingly, you can see in the red here, these 2 molecules, which are actually the one has been identified very recently, cyanonaphthalene. 1 cyanonaphthalene and 2 cyanonaphthalene, which I have marked here, they have just identified. And also you can see C60 fullerene, C70 fullerene, and C60 cationic fullerene. All these things have been identified in last like 5-6 years. Well, actually fullerene have been identified in 2010, so it's almost 11 years, but C60 plus, I mean, cationic fullerene has been identified sometime around 2015 or something like that. So now, also here, I can show you there are several other small molecules which have been identified so far in space using telescope. So in the region of electromagnetic spectrum, there are several telescopes which have been launched in space, and also the ground-based observations in covering the full electromagnetic region. Now, in this case, I can show you one of the telescope, which is name is Herschel, which was launched in 2009, and it is decommissioned now. In 2013, it was decommissioned. So it had a spectrometer is called HiFi, heterodyne instrument for far infrared studies, because the far infrared region, so basically you can understand, like when you want to study identify a molecule, you have to go in the microwave region, or if you want to study the molecular vibration, you can go for the, I mean, for the identification purpose, for the skeletal motion of the molecule, you can go in the far infrared region. So that's why this telescope had this dedicated spectrometer, which identified several nice structure like this. So you can see this is the complex organic molecules in the interstellar medium, which consist of water, and there are several small molecules have been identified with this HiFi spectrometer. So, and this is the what this spectrometer has studied the Orion Nebula, the famous nebula which has a lot of chemistry in it. So when you want to detect a molecule in ISM via microwave spectroscopy, what you have to think of, do the molecule have a permanent dipole moment? If the molecule has a permanent dipole moment, yes, the answer is yes, you can do it. But if not, sorry, you cannot do that. Like for example, in case of HCN, yes, because it has a cyano group, so this molecule is strongly polar and therefore it has a strong dipole moment. So you can identify this molecule. However, the other one, say naphthalene, this is not possible to identify the molecule because it doesn't have a permanent dipole moment via infrared via microwave spectroscopy. So if you want to understand that, okay, how can I understand this molecule is present or not? So what you have to do, you have to think of a substitution. Can a substitution increase the polarity? So that is why I have showed you in the before slides, the molecule naphthalene with cyano substitution have been identified because it had a permanent dipole. It has a dipole moment. So because of the dipole moment, it was easy to identify. However, this one is not possible to identify via radioastronomy. So now from the radioastronomy, so we wanted to identify this kind of molecule. So as I told you, it is not possible via radioastronomy. Can we look for the other region of the electromagnetic spectrum to get some idea, okay, this molecule is present or not? This type of molecules are present or not? So that is where the infrared astronomy comes in the picture. So I have shown you here the famous Orion Nebula, and you can see this, the left one is the visible light spectrum obtained of the Orion Nebula, and the same Orion Nebula, if you see in infrared, you can see a lot of signature here. So that is where the whole things are coming. So you can understand every negligible detail of this illuminated picture, and then go for understanding that, okay, what's happening there, how the molecules are forming, their formation mechanism, their destruction, everything. So as I told you before, this polyaromatic hydrocarbon like naphthalene and pyridine, these molecules are identified and not actually their presence have been observed sometime around early 70s through their emission features, which are called as aromatic infrared bands, so AIBs. And in 1984, Selgren, she is the first scientist who said that these pHs, the molecules are of like 50 carbon atoms or even more carbon atoms, pHs, and these molecules are, when they absorb a UV photon, they become stochastically heated, and their temperature goes up to like 1000 Kelvin. And after that, sometime, so two group, one group is from French, the Léger and Pouget, they are the French group, and the Alamendola et al, so they are the group from NASA Ames. So they independently did the survey and studied and finally came to the same conclusion that yes, these are the molecules which are emitting bands around like 3.3, 6.2, 7.7 microns, 8.6, 11.3, 12.7 micron. And here in the left, I have shown you all the spectrum which have been observed for the Orion Nebula. Okay, so finally, what are we going to learn out of it? If I know, okay, this molecule is there in the ISM, but finally, what's the take-home message for us? Okay, we want to know how much carbon, because carbon is the basic, I mean, one of the basic component of life. So how much carbon is locked in the form of pH? I mean, how much carbon, basically the cosmic carbon abundant in space, that can be learned because of from this kind of studies. Okay, so when I just told you, when a pH like pyridine, which absorbs a UV photon, it becomes stochastically heated, as I can show you here. And I did a small estimation of the temperature. Like, for example, if I put a photon of 5 electron volt to a pH like pyridine, its temperature goes up to like little bit more than 1000 Kelvin. So, and since the pH in the interstellar medium, they are isolated, so you can understand that, okay, what could be the temperature, because this is a microcanonical ensemble. So in that case, you can define the density of state of the molecule, and from there you can identify, you can calculate the temperature of the molecule. So, which is around 1500 Kelvin. So now I think you are convinced that pH molecule, when they absorb the photon in the interstellar medium, they are hot. Okay, after that, so once they are hot, it cannot be hot for infinite time. It has to come down, it has to relax. So how will they relax? In the ISM, the density of density of the molecule is very, very low. Compared to the laboratory, I can have couple of grams of naphthalene, couple of kilograms of naphthalene. If I want to buy, I can buy that. But in space, no, I don't have. So the number density in the molecule in the space is very, very less. So in that case, the relaxation of the molecule is only way via radiative process. If there are some other molecules, there could be a possibility for the collisional relaxation from the excited state to the ground state. But in this case, since the space is extremely isolated situation, so in that case, the only way to relax is via radiative process. So in this radiative process, I can show you when the molecule is absorbing a photon. So it starts from the ground electronic state S0 to a higher excited state, electronic excited state, that is S2, and then it does internal conversion. And after the internal conversion, it can do the fluorescence. And after the internal conversion, it can also do the IVR processes. And during the IVR processes, it actually emits the radiation in these wavelengths, which you have seen before, the 3.3, 6.2, 7.7, 8.6, 11.2 micron, 11.3 micron. And these are the bands which are called the aromatic infrared bands, which have been observed in space. So this is the way the AIBs are formed in space. And how these AIBs are affected. So if I want to know, okay, this AIB, the structure, all these details, so I need to understand more detail about the enharmonicity of the molecule, because the enharmonicity actually affect the position of the molecule of these bands. And moreover, the hot bands of the molecule creates additional asymmetry in the band shape. What is hot bands? I will come in a couple of slides and I will discuss you in more detail. So finally, what the astronomer wants to model the emission features, as I have shown you here and also in the before slides. They want to model that. So if they want to model, so they need some data from laboratory. So for that, one of the laboratory data has been presented here. So in this case, what the authors have done, they actually estimated the position of the band at various temperature and also the bandwidth at various temperature. So if I increase the temperature, the band position is shifting towards the lower wave number, and the bandwidth is increasing. So from the position of the band at different position of the band at different temperature, they can do a linear fitting. And from the linear fitting, the coefficient is the one which actually astronomer needs. So what is that equation they use? They use this equation for fitting the band position, and they use this equation for the bandwidth. So you can see this is just y equals to mx plus c. So that's a linear equation. And so basically what you need the value of m. So basically here the value of chi and chi prime. So if you give the astronomer, okay, this is the value of the chi prime and this is the value of the chi, they can try to model the emission features like the one has been done in the left, so Pesh et al. So basically they took the spectrum from a planetary nebula of 11.3 micron, and they can see, yes, this is kind of the modeling, this is the model spectrum. And however, there are several lacunas in this modeling, which we are trying to improve. And so for all these things, we need more and more laboratory data, which can give us so you cannot do one single pH and do the measurement and get this thing done. You have to do several pHs and get some idea from that. So for different bands and go for the modeling. And very soon, another very high resolution telescope called James Webb Space Telescope, which will be launched probably in 2021 in fall. And this telescope is actually dedicated to identify the pH in the far infrared region. So in this case, actually it is also in the mid infrared region. That's a big window. And you can see another it's a ground-based observation, but by in UK infrared telescope, which has given a spectrum, which is recorded a spectrum, and we can see there are a lot of signatures. All these marked signatures, these signatures are marked here. So if you want to understand what these signatures are, how do we understand this more detailed, you do need laboratory data, as I just told you. And especially when James Webb will go up, you will get more and more better quality result or space observations. So the problem, so the thing I told you that the molecule in the ISM, the pH molecule, they are not small like 10 atoms or 20 atoms. No, they are big pHs, like more than 50 atoms, 50 carbon atoms, yes. The problem of doing spectroscopy of these large pHs the first is you will not get them. Like if you want to make a pH of like naphthalene, if I don't know, if you are from the chemistry background, you know there is a synthesis mechanism like a Bardhan-Sengupta synthesis. You have to do several steps to identify to synthesize a molecule like naphthalene. So if you want to synthesize a molecule like 50 carbon atoms, it's a nightmare. So first of all, even if you can synthesize the molecule, you have to get the high purity. So if your molecule is contaminated with something else, so you will get all different types of wrong signatures which are you going to interpret. So first thing is that you have to get high quality pH, synthesize. And then if you want to do gas phase, basically this is the one you should do, because in the interstellar medium the things are isolated, so you should do gas phase spectroscopy. The problem of the gas phase spectroscopy is the moment you are going for large pHs, their vapor pressure actually reduces and it goes like 10-6 to 10-7 torr at room temperature. Therefore, in order to produce enough vapor in the gas phase, it's not possible. I mean, so if you have to heat very high, and if you heat them at very high temperature, they will polymerize, and then you will lose all the signatures. And then also for the gas phase spectroscopy, another problem is the atmospheric moisture and carbon dioxide. You have to maintain that. You have to remove the contamination from them. And finally, the interesting part is that in the laboratory, the vibrational and the rotational temperature are in thermal equilibrium, which we call as LT situation. So if the situation is LT, then it's unlike in the space. In the space, the rotational temperature of the molecule is like around 10 to 20 Kelvin maximum, but the vibrational temperature, just now I have shown you for like molecule like pyrene, it can go up to like 1500 Kelvin. So there is a strong thermodynamic non-equilibrium in the situation. So it's not in thermodynamic equilibrium, there is a non-equilibrium situation. So in this case, another approach is to do some solid spectroscopy of the large pHs, because first of all, in terms of the experimental protocol, like that, you can do the experiment much easily, because you don't have to vaporize them. You can make some pellets and then do the spectroscopy, and you can extend it to the high temperature. And also, if the rotation, I mean, if the solid state, then the rotation is freezed, because the molecule can only rotate if they are in the gas phase. So you will neglect the rotation part. So which is one way good, but I understand that in the solid phase there can be several interactions which can affect the bands. Yes, that's true. So with this thing, we started to do with this idea, we started to do the measurement in the solid phase and see, compare the result with some gas phase data, if available, and see that okay, how much we are deviating from the gas phase if we do the measurement in the solid phase. So what the data we need? We need the data from the feed chi prime and chi double prime. As I told you, these are the two things we need actually. So we did the measurement of pyrene in a microcrystal starting from 14 Kelvin to 723 Kelvin. And it's a cryocooling setup which can go from 14 Kelvin up to 300 Kelvin, the left one, and the right one is a high temperature, high pressure cell, which can go from 300 Kelvin to 723 Kelvin. Okay, so what we did, we put a pellet inside this in this setup, and pellet is made up of KBr and mixed with the sample, and then we took the spectrum for that, and this is the spectrum we have seen, we have observed. So here I have shown us 3 bands, like for example 6.9, 11.9 and 6.3. So you can see there are 3 different types of signature. If you notice the bands, one is relatively clean, I would say, not very clean, because it is just, this is a major component, but here there are 2 components here, and in this case there are 3 components. So basically we classified the bands in 3 different types. One is isolated band, low mixed band, and the highly mixed band profiles. And what we did, we measured the band position from the experiment at different temperature. So as you can see here, these all bands are associated with multiple substructure, hot band, and which are increasing with temperature, and band positions we determined, and then we are plotted here. So you can see, and we also did the linear fitting of the band position for these 2 bands, and these red dots are actually the gas phase data. you can see the gas phase data are reasonably going well with the solid phase measurement. And then what we did, we made a table like this. Okay, so band position at 300 Kelvin, and you calculate the chi prime from this work and chi prime from the gas phase. So you can see for bands like 11.9, 9.1, 8.4, 6.9, all these bands have very close match with the gas phase data. So which tells that good agreement between the gas phase work and the previous and this measurement, and the solid phase enharmonicity factors for large number of bands obtained compared to the gas phase data. So basically gas phase data, as I told you, the bands will be highly contaminated because of the moisture, atmospheric moisture and carbon dioxide. So from there to dig the information of spectroscopic information is very, very difficult. And it can be extended to larger pHs. That's the most important thing. We don't want to do a small pH like pyridine, because pyridine cannot be there in the space. So what we want to do, we want to test the hypothesis with pyridine and then use the hypothesis for the large pHs. So we already got some large pHs. We have chemists here. So they are very kind to give the pHs of moderately good quality of the spectrum. So with this, and then we decided that, okay, since we have the gas phase, we have the experimental data, why not doing some theoretical simulation to understand, okay, does this measurement going along with the theory or it's off with the theory? So for that, what we did, we took naphthalene, for example. And so, for example, for naphthalene, I can show you there are 48 vibrational motion, and this is the harmonic spectrum of the naphthalene. So you can do any kind of program like standard packages like Gaussian or any kind of packages which can give you the harmonic spectrum, and you can do the enharmonic correction too with this. But remember, these are all for 0 Kelvin. So you are not taking into account the temperature. So what we did, we calculated the enharmonic infrared spectrum of pyridine at using two different methods. One is called enharmonic Gauss, another is called Dimon nano. So enharmonic Gauss is a purely ab initio approach, and it considers couplings between the modes and all sorts of resonances. And Dimon nano is a standard approach, which is more like is a molecular dynamics approach, and both method has its plus and minus, negative point. So we wanted to see that, okay, how much we can go with that. So with this, I just told you that what is the hot bands. I would like to introduce you with this. So for example, so these are the vibrational states of a molecule. So if you have, so for example, if a molecule like naphthalene, it has 48 vibrational mode, there will be 48 zeros. So that means this is the ground state. Now, if you put one quanta in any one of the state, that's the first fundamental. So you will talking about the transition. So you will say this is a fundamental transition. So basically you are putting one quanta here. So that's a fundamental transition. That's called cold band. This is not a hot band. And because at the room temperature, always the ground state will be most populated. So the transition will be always happening from the ground state to first excited state. And same thing for the overtone. So you are putting two quanta. But if you increase the temperature, in that case, what you are going to do, you are populating the higher vibrational states, and you are likely to observe the transitions from those higher vibrational states to next high vibrational state. For example, in this case, third case, you can see there is a transition from this state to a state which has one quanta in first mode and in one quanta and another quanta in some mode. I don't know which one. So another mode. So that's the hot band. So these are the hot bands. Actually creates the asymmetry in the band shape, as you have seen in the astronomical spectrum. So we need to take into account the effect of hot bands. So what we did, we simulated the infrared spectrum of pyridine at 14 Kelvin and 300 Kelvin. And you can see at 14 Kelvin, the spectra is pretty sharp, clean spectrum. There is not many contribution, but the moment you are going at high temperature, several features are coming, and these are actually the hot bands. So these features are present, and that's why the bands are getting broad and their interpretation is becoming difficult. So what we did, we just took, these are the raw spectrum, this is the raw spectrum, and we just convolved with some Gaussian features. And you can see with increasing temperature, the bands are moving towards lower wave number. So what we did, we again did the same study. So basically these black points, these are the points from the enharmonic chaos. And these points are from Dimon nano. So basically the idea for using Dimon nano is the enharmonic chaos, this calculation, which takes into account for the several hot bands and all these things, this works reasonably well for up to moderately high temperature, like 500 something Kelvin, we used it here. But beyond that, it is possible. It is possible if you have enough resources, computer resources. But because of the computer limitation of the resources, we could not go beyond 500 Kelvin. So what we did, but as I have told you that astronomical pHs, they are very high temperature, like 1500 Kelvin. So we need to get that information. So what we did, we used another one, which is called Dimon nano, which can be extended up to up to like 2000 Kelvin even if you want. And we want to make a smooth transition if it is possible from transition. So if you want to model the spectrum at the low temperature region, you can use enharmonic chaos. If you want to go for the high temperature, very high temperature, you can go for the Dimon nano. And then we compared our data with the gas phase again, if available. So you can see this is the plot. This is the in this figure I have shown you, in this table I have shown you that okay, for many bands we can see the band positions, the enharmonic factor are close by with the experiment, but not always as usual. So for that, what we decided that okay, so the enharmonic chaos, this deriving enharmonic factor for quantifying the infrared band position at temperature, and they are not, I mean, a part of good agreement with the MD and part of the good agreement with the molecular dynamics simulation. But the thing is, for the molecular dynamics simulation, you will get the band position at various temperature, but what will you lose? You will lose all spectroscopic information. Like for example, if you do enharmonic chaos calculation, which is for the low temperature, you can see there are a lot of quantum chemistry in between. So you can say, okay, this state is coupling with that state, and all these things, all sorts of detailed quantum mechanical information you will get, which you are going to lose in MD. But finally, you are getting some information out of it. Okay, you are getting the chi prime and also the chi double prime at very high temperature for a molecule like pH, like pyrene. Even it can be extended to larger pHs, but for doing enharmonic chaos for large pHs, it's still possible, as I told you. But again, the problem will come for the computational resources. If you have good computational resource, it is, of course, it's possible. In principle, the code can do everything. I mean, you can just give the information it needs to run the calculation, it will do it for you. So, and then once we get this success, and then we decided, okay, let's do some measurement for the fullerene, because the fullerene is the other molecule which have been identified in space in 2010, and that time. In 2012, there is another group which have been studied that, okay, how the fullerenes are forming in the interstellar medium, because I told you the astrochemistry is not only for the identification, it is also about talks about the formation mechanism of the molecules in the ISM. So what it does in this paper, it has reported that in this is the position of the star, and it has scanned only this region. Okay, so it has found that region 2 is the spectra from this spectra. This spectra is from the region 2, and this spectra is region 1. And you can see the region 2 is close to the star. So star is here. So the star is here. So close to the star, you are getting more like C60 features, which is expected, because if you have the high radiation, then the CH bonds can break, and finally it can go and round up to fullerene. So in this position 2, you are getting more fullerene. However, in the position 1, it is far away from the star, so you will get mostly like pHs. So you can see here the pHs are in this position 1. So two group in 2010 actually, one group from Selgren and another group from Canada. So they identified fullerene first in 2010 in a reflection nebula. so which has both pH and C60 in the spectrum. And if you have the mixture of pH and C60, it's a bit difficult to identify that which is because of C60 and which is because of pH. So disentangle the information is a bit difficult. However, the planetary nebula, it doesn't have the pH because it's the later stage of the life. So planetary nebula forms at the end of the lifetime of the star. So in that case, you are going to have only mostly carbonaceous particles. So for example, like here, for the TC1 planetary nebula, C60, C70, all these features. So C60 features are marked here like this with red dots, and C70 features have been marked with the blue. So with this, then we thought that, okay, what actually the physical state of the molecule? So are they in the gaseous form or are they in the solid form? So according to the science paper in 2010, these groups argued that, okay, this pH molecule, this C60 molecule is probably in the solid phase, in the ISM embedded on the dust particle. And this other group in 2010, they said that most likely to be there in the gaseous phase. So there is a big controversy in between these two groups. And so therefore we decided, okay, can we use again our infrared spectroscopy to say something more about this physical state? So you can see this blue spectrum is the observation from TC1, thanks to Ian Kami who provided us the spectrum, and this is the laboratory spectrum. So you can see this so fluorine has because of this symmetry, it has only 4 infrared active bands, even though it has big size, but it has only 4 infrared active bands, which are at 7.0, 8.5, 17.4, and 18.9. These are the 4 infrared bands you will see in case of fluorine. So that's what you can see also in the experiment. However, there is a small band here around 6.5, which is the only combination band of fluorine which have been identified in space. And we do see the same band in the experiment. So what we did, we again use our infrared spectroscopy to get the band position at various temperature. And then what we did here, we plotted the band position at various temperature, and we see our experiment and our observational band position, which is in the black. So the region where it actually intersect, that could be the position, that could be the temperature of the molecule. So since I have the band position, so I know the band position. So if I put the band position and where it will intersect my plot, that could be the band position at that could be the temperature of the molecule. So I used for 7.0 micron, 8.5, 17.4, but 18.9 for so you can see for these two bands it's going well, but for these two bands it's not at all. Even for this one it is terrible. So it's actually going like very like around 500 Kelvin, and even for 18.9 it's going it's not physical. So then we decided that what could be the possible reason for this. So we also then we started to investigate that, okay, can we estimate the intensity of the bands for the 4 different bands. So then we identified we calculated the intensity and took the ratio, and for all bands with the intensity ratio gave us that, okay, more or less like 700 Kelvin, the temperature of the the effective temperature, I would say, of the molecule. So it's likely to be gaseous. But as you can see, because of this discrepancy, we are not super sure about our conclusion, but still we are ongoing on this project. We are still working on this project to understand it a bit more. Another conclusion we have also made, that because of the omnipresence of C70 along with C60, so if you do the measurement, so this band is actually a mixture of C60 and C70, as you can see here. So if you do a measurement with only C60, you are unlikely to retrieve the whole information. So that is where we are a bit puzzled now, and we are trying to improve our measurement and analysis. So if we can tell a bit more. And you can see the emission from fluorine comes from the cooling cascade, as same for like pHs, absorption of an UV photon, and emission from other fluorines, C70 might be present at lower level, affecting the profile of 17.4 and 18.9 micron, and therefore it calls for high precision gas phase measurement. So this was also done in the solid phase, so it definitely requires high quality gas phase data. Unfortunately, this high quality gas phase data for fullerene is not available because of so many vibrational modes. So you will not, if you take an infrared spectrum of fullerene by heating at like 900 or something Kelvin, you won't see anything because you are populating all higher vibrational states. So basically you will not see any transition which is from the ground state. So there you will lose all the information. So however, we do need that. So and also and not only the gas phase, again, if you do the spectroscopy in the gas phase, you will be populating both rotational and vibration, well, considering both rotational and vibrational temperature in equilibrium. But again, like I told you, in the space, rotation is cold, vibrational is hot. So you have to do the spectroscopy at non-LTE situation. Okay, so there, and also you need high quality space observation, which is not done yet. So probably GWST will go up in another couple of months. So we will get a good signature of pH C60 features, which will help us to identify the bands more easily. Relatively easily. And then the final part of my presentation about the shockwave processing of the interstellar dust analogs. So in the interstellar medium, the shock waves are generated because of several reasons. It can be generated from the bipolar outflows, or it could be generated because of the supernova. So once the shock wave is generated, how they interact. So in the interstellar medium, there are the molecules, there are the carbonaceous particles. All these particles are there. I have shown you that these molecules are there. So how they can interact with the shock wave, and finally what they are forming. So again, astrochemistry is talk about the identification, formation, and the destruction. So now I am just destructing that, okay, this molecule, when they're destructing, so can they form a new species, and what type of species they are forming? So that's actually the motivation of this study. However, I should be one point very cautious here. The shock study, what we do in the laboratory, they are pretty different than the interstellar shock. But the thing is that we are more interested in the chemistry, saying that, okay, if the shockwave interacts with the sample, it produces some material and it can give us some spectroscopic signature. So for that, we have a collaboration with IISc Bangalore, and this is the shock tube setup at IISc Bangalore, and this is the driver section, and this is the driven section. Many of you are already acquainted with this kind of setup. So what we do, we put our sample at the end, close to the end flange here, and then what we do, we burst the diaphragm with high pressure helium at around 30 to 40 bar of helium, and the shock wave is produced. And then the shock wave goes to the near to the end flange, and then when it comes back, the reflected shock, it actually interacts, and the reflected shock temperature is very high. So when it interacts with the sample, it will give us some spectrum. So this is something. So this has been this is the situation of the diaphragm before the shock and after shock, and you can see after shock, this portion is completely black. So all this. So what we did some ex-situ measurement with this at some point. So what we found that if we do some XRD measurement for this is for fullerene with hydrogen in the shock tube. So when it is without shock exposed, it's strongly crystalline. But the moment you are exposing with shock, it's going more and more amorphous in nature. So you can see the peaks are actually going out, so becoming more and more amorphous nature. So basically, it's likely to be more graphitic nature. And also what we did, we took the infrared microscopy to see that, okay, in presence of hydrogen, C60, can it form some carbonaceous like aromatic species? So I told you in the beginning that this pH, if you start from pH, if you induce with high radiation, UV radiation, you will go to C60. But if you expose C60 in hydrogen, can it form some small pH or aromatic species? We don't know. So that's why we did this measurement. But unfortunately, our proposition didn't go well with us as usual, expected from the experimental science. And so we thought that we will get some signature. So if there is some aromatic species formed, then I should get a band around 3100, close to that. But unfortunately, we didn't get much good signature here. However, we did observed the bands around 2900 wave number, which are actually because of aliphatic molecules. So if you expose C60 in hydrogen, you are likely to get some aliphatic signatures, aliphatic molecules which have been formed during the exposition. And then we decided that, okay, these are all about ex situ stuff. So can we do the measurement in situ? So the moment when the shock will interact, that time if I can record the spectrum, can it give us some information out of it? So what we did, sorry, 1 second, I missed it, one point, that's we did the Raman measurement also. And you can see for the Raman measurement, this sharp band when it's the unexposed sample, and the moment you are giving exposing the shock, you are observing the two other G bands of the of fullerene and becoming is more and more amorphous in nature. So which actually going with the proposition that when you expose fullerene with shock, probably it is becoming more and more amorphous. And then, as I was talking just now, that about the in situ spectroscopy of shock exposed interstellar dust and all. So what we did, we so close to the sample chamber, now we have fixed a spectrometer. So you can see here this part where we have fixed a spectrometer and connected with the fiber optics in this part, and the sample is just here. So in this part where the sample is, so when the shock is exposing with the sample, it will forming some radical maybe, and that light we want to capture. That's what we wanted to do. So what we found, these are the signatures, which is the real-time measurement. As you can see, this is the bands. These are the bands of C2 emission features. And these are the different vibrational state. Delta V equals 0, delta V equals R, delta V equals minus R, minus 2. So current and another interesting part, all these bands are a bit shifted. You can see there is some broad continuum here. So we are still working on this data. So we recently concluded that this broad continuum is probably because of the black body emission of the carbonaceous particle. So when the shock wave is exposing with the carbonaceous particle, and actually we observe this type of emission, this kind of broad continuum, whenever we are using a carbonaceous particle. When we are exposing shock to a non-carbonaceous like silicates, we never observe this type of thing. So this type of broad emission. So it's bit shifted from the baseline. So we recently understood that this is because of the emission from carbonaceous, small carbonaceous particles, and it could be some carbonaceous soot or some other carbonaceous stuff. So and then what we did, we fixed our monochromator, and we at a specific wavelength. So this is the wavelength 510 nano wave number, and then we see the decay profile of the wave at that specific wavelength. So you can see this wavelength is going down, but here it's a tailing. So again, it goes to our proposition, probably this tailing is because of the black body. So extended emission, this is just because of the black body emission from the carbon particles. And interestingly, it has been observed in space that carbon nanotube in space. So we have exposed silicon carbide in shock, and we have observed the presence of carbon nanotube. And the carbon nanotube has been identified in space. I mean, it is there in space in the ISM. So we have compared our data with the molecular dynamic simulation that we have found in the molecular dynamic simulation. It tells that when you are exposing, we are breaking the C60, so it goes via emission of C2, and that's what we have seen here. So if it forms C2, then we should see that, and that's what we have seen. We have seen the formation of C2 here. So this data is still, we are processing, and we are computing the spectrum of C2 at very high temperature, at very high pressure. And soon probably I will show you some results maybe the next time. And then I would like to acknowledge my co-workers and my colleagues. And first of all, I would like to acknowledge my grant from NanoCosmos ERC grant, and then my previous research organization where I was working in IRAP, and currently I'm in IPR, Institut de Physique de Rennes. and then University of Rennes 1, and they are my colleagues, and from Toulouse and Cagliari. So Giacomo and Matthias, they are the one who are helping me for doing the theoretical part, and other group is for the experimental. And my current research group at University of Rennes. And finally, I would like to thank all of you for your kind attention. Thank you.
Thank you, Dr. Shubhadeep, for your wonderful and fascinating research and presentation. Now the floor is open for doubts. You can ask any, if you have any queries and clarifications, you can ask them. The organizer can unmute the mic of the participants, then they can be able to ask the questions.
Dear participants, just unmute your mic, then you will speak. Your queries will be clarified. Shiva, unmute பண்ண முடியாது.
Dr. Shubhadeep, I have a small basic doubt. Shubhadeep, can you able to hear me? Hello.
Yeah, yes, can you hear me?
Yes.
Sorry, yeah.
I have a basic doubt. Actually, you have generated shock by using a shock tube. It gives the temperature around 4,000 Kelvin, right now. By using this shock, actually, you have exposed to that carbonized particle, and you got amorphous, right? But actually, the shock in the interstellar medium, interstellar space is actually huge than the shock what you have generated.
Exactly.
Then can I assume actually that
exactly
we cannot find any crystalline particle in the space?
As I told you during my presentation, that people have seen graphite-like structures, like first of all, carbon nanotube, and also graphite-like signatures in space. So it yet to be investigated. So maybe it's possible. So the crystalline particle, so it depends which region you are actually taking your spectra from. If you are taking a spectra very close very close to a shocked region, so then maybe you are right. But if you are going far away, so in relatively new stellar surface, so in that case, maybe I don't know. So it has to be still investigated. But you are right, from our experiment, as I told in the beginning also, this shockwave and the shockwave produced in interstellar medium, they are very, very different. But finally, we are interested to see the morphology changing with the particle and the new species. But as your question is about saying if the molecule is purely, there is no possibility for getting crystalline material in the space, I think it has to be investigated, because there are several comets which have the particles crystalline. So it has to be investigated still.
Okay. One question from the participant. Two questions are there. Shockwave induced amorphous nature of the fullerene phase transition belongs to topological disorder or destruction of crystal structure?
This is the destruction of the crystal structure. So basically, it's actually destructing the crystal and then forming more amorphous, like graphitic material, probably.
Okay. One more question from Shiva. How we can identify the permanent dipole moment of a molecular structure by just looking the structure of the molecule?
Okay. So in this case, 1 second, give me 2 minutes. Sorry. So for example, if a molecule has a group attached to it, which is highly electronegative, for example, here, you can see there is a presence of nitrogen. So hydrogen cyanide, so there is a presence of nitrogen. Nitrogen group is attached. So CN is strongly polarizing. So definitely this one, just looking at the molecular structure, I can say that the dipole moment will be in this direction, towards right, because nitrogen is strongly electronegative. So by looking at the structure, I can say if the molecule has some electronegative substituent with it, like for example, if you take the CN out from here and put it here, then again it is becoming more electronegative towards this side, so it will have some dipole moment. But if you take, like, if you replace the hydrogen with some oxygen and with the oxygen and this nitrogen with the oxygen atom, then again it doesn't have any dipole moment, because one dipole moment is acting in this direction, other dipole moment is acting to other direction. So basically they will nullify the two vectors. So they will nullify. So in that case, you can just see the molecular structure and see if it is having a permanent dipole moment or not. So in this case, they have a permanent dipole moment. But sometimes the molecule may generate instantaneous dipole moment during the vibration. So even the molecule is not doesn't have a permanent dipole moment, but during the vibration, it can generate a dipole moment because of the asymmetry in the vibration. So just looking at the molecular structure, yes, you can do it. You have to look for the electronegative substituent or for the permanent dipole moment, or you can, even if the molecule doesn't have a permanent dipole moment, look for the vibrational motion if it is forming instantaneous dipole during the course of vibration. That's possible.
Thank you, Subhadeep, for your wonderful and highly informative lecture. I hope many people got many doubts, but still due to the time constraints, just I would like to conclude this session. Thank you so much, Dr. Subhadeep Chakravarti, for your wonderful and informative talk. Thank you so much. Also, I thank the organizers, especially Dr. A. Saranraj, for giving this opportunity to be with you. Thank you, and thank you. I thank the participants also for their wonderful cooperation. Thank you. Thank you. Over to the convener.
Thank you. Thank you so much.
Thank you. Thank you.
It is a real pleasure listening to you, sir. And on behalf of the organizing committee, I extend my special thanks to Dr. S.A. Martin Vitodas for being the chairperson. Thank you, sir. Participants, now we start the remaining oral presentation. First, we start with CG1. Before that, a kind note to all the participants. The annexed link will be sent in chat box. Do please. Now we start the oral presentation with CG1.
Good evening to everyone. Now we start on CG06. Dr. V. Vitrivelan. Sir, Vitrivelan, sir. Vitrivelan, sir, is available. So please respond. far is not there. Next to go on CG08, Subhash Chandra Bose.
Sir.
Just a minute, sir. I'll share the screen.
Shall I? Sir, am I audible?
Sir, just a minute.
Okay, no problem. Okay, no problem, sir. I'm waiting.
Screen is visible, sir?
Yes, sir. Second slide.
Okay, let's start. Shall we start?
Okay, sir. Thank you. So, good evening to all. First of all, thanks to the organizers of NCIST conference. Now, I'm starting my presentation. I'm Subhash Chandra Bose, research scholar, MD College. I'm doing PhD under the guidance of Dr. K. Balasubramanian. So my work is crystal growth and characterization of 2-aminopicolinum 4-hydroxybenzoate single crystals. So next slide. So next slide. Okay. This is content of my work. Why I'm choosing 2-amino-4-picolinum? That's the reason behind this work in the first slide. Then the introduction about the organic materials. Then reaction scheme of 2-aminopicolinum 4-hydroxybenzoate crystals and their characterization, results, and discussions. Finally, I concluded my work. So next one. Before I start my work, I studied a literature survey about 2-amino-4-picol material and their characterization and collected some of the works from 2010. From 2010, 2-amino-4-picolinum 4-aminobenzoate. From 2011, 2-amino-4-picolinum toluidine sulfonate, 2-amino-4-methylpyridinium tartrate monohydrate, 2-amino-4-picolinum nitrophenolate nitrophenyl from 2015, and from 2019, 2-amino-4-picolinum 2-chloro-4-nitrobenzoate. All these materials are grown as single crystals and their properties were studied. Next, sir. So introductions. The material has large nonlinearities in frequency conversion. It's the applications of telecommunications and optical information processing. So all the organic materials have their fast and large nonlinear response curve over broad frequency range. 2-amino-4-picolinum is a very good proton acceptor. In the presence of carboxylic acid, it always deprotonate that group. So it has large optical damage threshold. 2-amino-4-picolinum 4-hydroxybenzoate is grown as a single crystal and is subject to various crystal characterization studies for nonlinear applications. So next. So this is the reaction scheme. I taken 1:1 molar ratio of 2-amino-4-picolinum and 4-hydroxybenzoate acid. Both are 99% purity. 4-hydroxybenzoate acid was dissolved in methanol, and then I added 2-amino-4-picolinum. It works in manganese around 2 to 3 hours and grow up to 30 to 40 days. So 40 days. 2 amino 4 picoline grows a proton from the acidic solution and form that crystals. The next. So characterization. To find out the crystal system and lattice parameters and some other points from the single crystal XRD and the powder X-ray diffraction, where nuclear magnetic resonance analysis, FTR, UV visible NIR study 2, study about optical studies, and then thermal analysis to find mechanical stability at room temperature of microharness and non-linear optical studies. Sir, X-ray first one, before slide. Next one. So no, before one, results and discussion. Single crystal XRD study. Next slide.
Sir, I think the slide is blank. We don't have it.
Okay, sir. I'll tell you. So this is a monoclinic crystal system. Their space cube is P21 bar C. Their unit cell dimensions A is equal to 13 Armstrong, B 9.13 Armstrong, C 11.43 Armstrong, and alpha, beta, gamma value. The alpha and gamma is 90 degree. Then beta is equal to 112.7 degree. From powder crystal XRD pattern, we confirm the material. And then morphology, 001, 001 bar, 1, 2 bar, 1 bar. There's some of the morphologies having. In NMR spectral analysis, in H NMR spectrum and C NMR spectrum, dimethyl sulfoxide is a solvent. In methyl proton in 2.27 and aromatic CH protons, wherein 7.15 and 7.562, 7.63 and 7.862, 7.88 parts per million were. In hydroxyl proton and methyl carbon is 9.62 parts per million and 20.7 parts per million in methyl carbon, and quaternary carbon in 114.4 parts per million, in which the carboxylate group was attached. So next one. Okay. Then UV NIR spectrum of my work. The sample weight is, sir, I think. Sir. So there is no screen.
Sir, நீங்க அனுப்புன ஸ்லைட்ஸ்ல எங்களுக்கு அப்படிதான் சார் ரிசீவ் ஆயிருக்கு.
அப்படியா?
Yes sir.
இல்ல சார். இன்னொரு அனுப்பட்டா டக்குன்னு.
இல்ல சார், நம்ம பின்னாடி ஆப்ஷன்ஸ் பார்ப்போம் சார். ஜஸ்ட் நீங்க அப்படியே கன்க்ளூட் பண்ணிடுங்க சார்.
சரி, ஓகே சார். சார் நம்ம ஸ்லைட் கம்மியா கம்ப்ளீட் பண்ணுங்க. அவ்வளவுதான் இருக்கல. இருக்கிற ஸ்லைட் கம்மியா நான் எக்ஸ்பிளைன் பண்ணிடுறேன். So this is thermal analysis of sample weight has 5 milligram. Then temperature range 25 to 260 degrees Celsius. Heating range is 10 degrees Celsius per minute. Melting point is 173 degrees Celsius. Below 182 degrees Celsius, there is no endothermic and no exothermic peak. At 183 degrees Celsius, it has endothermic peak. The major weight loss starts from 183 degrees Celsius to 220. Complete weight loss after 220 degrees Celsius. To the loss of carbon dioxide and CN, there is no phase transition below the melting point. So next slide. So this is Vickers microharness test. The graph between load and microharness number. If the load increases, there also the microharness harness number also increases. The load range from 10 to 100 gram. Harness number increases also up to 100 gram. After 100 gram, that is beyond 100 gram, there is some breakage. So indentation was made on 001 surface. So work hardening coefficient is 2.2. So be less than 1.6, that is hard material category. Greater than 2.2, It's a soft material category. So my material has 2.2 work hardening coefficient. So it is a soft material category. It's a rising reverse indentation effect. So next one. This is the horn. The Z scan. So closed aperture and open aperture. So I find out this is a second harmonic generation or a third harmonic generation. So I find in single crystal XRD, this is monoclinic system and space group as P21 bar C. So space group P21 bar C is the symmetry group, that is third harmonic generation, and are confined in Z scan. So in closed aperture, there is pre-focal peak and a post-focal valley. This is self-defocusing. Nonlinear refractive index is N2 and nonlinear optical absorption coefficient beta. Third order nonlinear susceptibility is X. So open aperture Z scan curve is a multi-photon absorption, is a transmittance, as a normalized transmission. It's a nonlinear. Okay. So finally, I concluded my work. So good quality organic crystals of 2-amino-4-picolinum 4-hydroxybenzoate are grown by conventional slow growth technique. It crystallizes in monoclinic system and their space group is P21 bar C. It is a third harmonic generator. The grown crystal transmit 50% in UV visible spectrum. It belongs to the soft material category. Under the microharness test, the nonlinear co-absorption coefficient is 0.25 in 10 power minus 4, and third order nonlinear susceptibility is 6.22 in 10 power minus 6. So crystals can be in nonlinear optical limiting applications. Thank you.
Thank you, sir.
Thank you.
Now it's time for a discussion.
I have one question. And what is mean by reverse indentation size effect? You can tell in hardness RISZ, na?
Yes,
reverse
sir.
indentation size effect. What is mean by reverse indentation size effect?
So for load increases, the hardness number also increases. Then the crystal structure and chemical bonding were broken. Okay, that is size is reverse indentation size effect type.
Okay, and that's all my side. Any other questions? Audience, let you ask.
So one more question. Your grown crystal belongs to soft category material, right?
Yes, sir.
So that material, how it can be a potential material for device fabrications?
For device fabrications.
Since generally device materials requires hard material, no?
No, sir. All of the hard materials cannot code in device fabrications.
Yes, right. Okay.
So their transference category is 50%.
Okay. So what about the mechanical stability?
Mechanical stability is soft material.
Soft category material, right? Yes. So then soft category materials are how can be a potential material for device fabrication? Since device, when we go for device fabrications, so all the characteristics should be in high norm.
No, sir.
So
in the
high efficiency, high mechanical stability, high thermal stability, right?
Yes.
High mechanical stability. So your material belongs to soft category material. So then how it can be a potential material for that?
Sir, in the thermal analysis, we have in boiling point up from 183 degrees Celsius.
Okay.
So we can stabilize up to 183 degrees Celsius.
Okay. Okay. Thank you.
Is boiling point or melting point?
Sir, melting point. Sorry, melting point. Boiling point is not 183 degrees. Melting point.
Yeah. And the many PPT is mistakes in your PPT. Please correct it.
So one more question.
Yes, sir.
So can you go for mechanical stability plot, right? Mechanical plot, mechanical stability plot. So what is your interpretation with respect to load?
Yes, sir.
Yes, sir. Can you explain with respect to load? With respect to load, the hardness is increased, right?
Yes.
How it can be said? With respect to low, when we given the low high stress to the material, the mechanical stability should be reduced. So, but your interpretation is increased, right? So, how you can correlate these two things?
There is a one formula.
Usually, when we increase the pressure or temperature or stress, the material stability should be reduced. So, okay, sir. Check it now.
Okay, now I check it and tell
Do
you.
you have crystal image?
Sir?
Do you have crystal image? You can
Yes,
go
sir.
on.
In the single crystal XRD, I have crystal image. That
Sure.
slide was missing. That slide
Don't
is
see-
missing, sir. Yes, the slide is missing.
Okay.
I'll send you, sir.
Okay, no problem. And what is the dimension for your ground crystal, and how many days you can got that crystal?
Sir, around 40 to 50 days.
40
in
to
winter, but in the summer, around 20 to 25, 20 to 30 days, it will grow.
Why? Why it will be differ?
Sir,
Is
because
there
of it's a large vaporization. Sorry, evaporating rate. In winter, we have no.
And what is the dimension for your ground crystal?
Dimension.
And what is the color of your crystal?
Sir, colorless, sir.
Colorless.
Yes, sir.
What is the size and shape? It is needle shape or
Sir, it's a cube shape, sir. Some cube. Little cube.
Okay. Okay, no problem. Thank you.
Thank you.
Thank you, sir,
Thank
for
you, sir.
your nice interactions.
Thank you, sir.
Now it's for 09, CG09. Sahai Infant from SSN institution. Complex. Okay, thank you.
Once again, a warm good evening to one and all. We thank the judges for the evaluation, Dr. J. Tirupati and Dr. S.A. Martin Vitodas for your valuable presence. Thank you, sirs. Today's section is over. We start tomorrow's section exactly at 9:30 a.m. So be present on time. The link will be sent tomorrow morning through the WhatsApp group. Thank you, everyone. Have a pleasant evening.
And thank you so much for the given opportunity to convener Dr. A. Saranraj. Thank you, sir. Thank you so much.
Thank you, sir. Welcome. Sir, Brito, sir. Sir, thank you, sir, for your
Thank
support.
you. It was good. Well done.
Okay, thank you, sir. Thank you so much, sir, for your support. Dr. J. Tirupati, thank you, sir. Thank you so much for your support. Dr. M. Manivannan, thank you, sir. Thank you so much for your support. Thank you all the participants to meet the tomorrow at 9:30 a.m. Thank you so much.